What if the universe you see around you, the trees, the sky, the laughter of people, even your own heartbeat, is not truly physical, but instead the unfolding of a vast mathematical equation? It sounds impossible, like a thought experiment only philosophers or theoretical physicists would dare to explore. Yet, many of the greatest scientific minds, from Pythagoras to Galileo to Max Tegmark, have suggested that reality might be nothing more than mathematics wearing the mask of matter. The patterns of physics, the strange precision of constants, and the hidden order in chaos all whisper the same possibility, that existence itself is made of numbers. If this is true, then every star in the night sky, and every thought in your mind is not a thing, but a solution, a piece of math playing itself out. Today, we dive deep into this radical possibility. From the very beginnings of civilization, human beings have been obsessed with patterns. When early humans gazed at the stars, they noticed not just random lights but constellations, repeating cycles, and predictable movements. The moon swelled and shrank with perfect rhythm. The seasons shifted with reliable timing. Even the chaos of rivers, storms, and crops seemed to follow cycles that could, if one looked closely enough, be anticipated. These early recognitions of order became the seed of something extraordinary. The idea that beneath the messy surface of life lay something hidden, something structured, something numerical. The Pythagoreans, followers of the ancient Greek philosopher Pythagoras, were among the first to suggest that numbers were not merely human tools, but the fundamental essence of reality itself. For them, mathematics was not a language invented to describe the world, it was the language the world was written in. They discovered that the pleasing harmonies of a lyre's strings could be expressed with ratios. One string twice the length of another produced a perfect octave. To them, this was not coincidence. It was evidence that numbers shaped the very structure of the cosmos. All is number, they declared, a phrase that echoes through centuries of thought. Consider how radical that idea was. For most of human history, people believed the universe was built from earth, water, fire, and air, physical substances you could touch and see. But the Pythagoreans claimed that the foundation was something invisible, intangible, abstract mathematics. To say that reality is number was to say that matter itself is secondary, a consequence of deeper, immaterial rules. Imagine telling a farmer in 500 BCE that his fields and crops were not truly earth and grain, but at some deeper level, equations unfolding. It must have sounded like madness. And yet, the more one looked, the more the madness seemed true. Even Plato, in his philosophy, leaned toward this view. In his famous theory of forms, he suggested that the physical world is merely a shadow of perfect eternal realities, the mathematical form of a circle, more real than any circle drawn in the sand. He believed that mathematical truths existed in a timeless realm, untouched by decay or imperfection, and that our physical world was simply an approximation of these higher structures. For Plato, learning mathematics was not just a matter of calculation. It was a spiritual act, a way of glimpsing the divine architecture of existence. Fast forward to the Renaissance, and you find Galileo declaring, "The book of nature is written in the language of mathematics." He argued that without mathematics, reality was incomprehensible, like trying to read a book without knowing its alphabet. The shapes of planets' orbits, the fall of an apple, the curve of a rainbow, all of these phenomena obeyed laws that could be expressed as equations. The more scientists uncovered these patterns, the more persuasive the idea became that reality itself is mathematical at its core. If nature were chaos, why should equations describe it so perfectly? But this raises a haunting question. Are we merely using mathematics as a convenient human-made tool to describe what happens, or is mathematics truly what the universe is? In other words, do equations just map the world, or are they the fabric of the world? To answer this, consider how astonishingly universal mathematics is. An equation discovered in one domain often finds unexpected application in another. The same formulas that govern sound waves also describe the behavior of light. The equations that describe planetary motion also whisper in the tiny world of quantum particles. Mathematics is not just useful, it is eerily universal. Even stranger is the way mathematics seems to predict truths before we even encounter them. The existence of black holes was once simply a mathematical prediction from Einstein's equations. The existence of antimatter emerged from the structure of mathematical physics before it was ever detected in the lab. Time and again, mathematics has not merely described the world we know, but revealed worlds we did not yet know existed. How could this be, unless reality itself is in fact mathematical? Think of it this way, If reality were fundamentally random and messy, our mathematical descriptions would eventually fall apart. We would expect equations to fail, constants to wobble, and predictions to crumble. And yet, across centuries of discovery, mathematics continues to hold, not just roughly, but with uncanny precision. The gravitational constant, the speed of light, the fine structure constant. These are not just numbers, they are the precise scaffolding that makes reality possible. Why should reality be so exact, unless it is mathematics playing itself out? This obsession with numbers, born in ancient Greece, has become the foundation of modern physics. From quantum mechanics to cosmology, our deepest theories are written in equations. And while one might think this is just a language we've imposed on the universe, the strange predictive power of mathematics suggests otherwise. It is as if we are not inventing math, but discovering it, uncovering rules that exist independent of us. Rules that were there long before humanity looked up at the stars and wondered. And so, the ancient dream of numbers still haunts us today. Perhaps Pythagoras was right all along. Perhaps everything, your body, your thoughts, your loves, the galaxies spinning overhead, is nothing more than mathematics, manifesting itself as reality. If that is the case, then when you look at the world, you are not seeing matter at all. You are seeing equations written in the language of existence. Plato's philosophy has often been described as a bridge between myth and mathematics, between the poetic stories of the ancient world and the cold precision of abstract reasoning. At the heart of his thought lies the idea of forms, timeless and perfect realities that exist beyond the messy, imperfect world of the senses. And for Plato, mathematics was the purest gateway into this realm. A circle drawn in the sand may wobble, its edges uneven, its shape fragile against wind and time, but the form of a circle, the perfect mathematical idea of roundness, exists beyond space and time. It never decays, never bends, never fails. It is absolute. Plato argued that the physical world we inhabit is merely a shadow, an echo of these higher realities. The chair you sit on is imperfect. It might wobble, splinter, or fade, but the concept of chairness, the mathematical proportions that make something a chair, belongs to a realm untouched by impermanence. To study mathematics, then, was to touch eternity. When students in Plato's academy carved numbers and geometry into wax tablets, they were not just training in calculation, they were preparing their souls to glimpse the divine blueprints of reality. This perspective planted a radical seed. Perhaps reality itself was not material first, but mathematical first. Plato was suggesting that the truest things are not atoms, not substances, but abstractions. His world of forms is eerily close to the modern notion that mathematics itself might be the foundation of existence. When you think of a triangle, the one you imagine in your mind is far more precise than any drawn on paper. It exists in a realm of perfect truth, untouchable by human flaws. If such perfection exists in mathematics, could it not also underlie the entire universe? Consider how mathematics behaves compared to everything else. Empires crumble, languages shift, cultures die, but the Pythagorean theorem remains. It does not care whether it is inscribed on clay tablets, chalkboards, or computer screens. Its truth persists across time, cultures, and minds. Plato saw in this an echo of the eternal. If mathematics does not change, and if the world of matter is fleeting, which one is more real? Plato's answer: the numbers, the equations, the forms. This way of thinking had consequences far beyond philosophy. It influenced how Western civilization approached science, art, and even religion. Architecture in ancient Greece, and later in the Renaissance, was guided by the search for ideal proportions, ratios that mirrored divine harmony. The idea that beauty itself could be reduced to mathematical ratios, the golden rectangle, the perfect symmetry, came straight from this Platonic vision. When you stand before a cathedral's arches or gaze at the spirals in a seashell, you are seeing echoes of this ancient conviction: mathematics is the skeleton of beauty. But Plato's perfect forms also raise unsettling questions. If reality is built upon mathematical ideals, then what does that say about us? Are we merely imperfect shadows of higher truths? Is your very identity nothing but an approximation of some timeless equation written beyond space and time? If so, then what we call reality may not be reality at all, but a blurred reflection. Perhaps we are like prisoners in Plato's famous allegory of the cave, mistaking flickering shadows for solid truths, while the true structures, the equations, the mathematics, exist outside our perception. Fast forward to today, and modern physics finds itself strangely echoing Plato. When scientists search for the theory of everything, What they are really searching for is a single unifying equation, a mathematical form so perfect it explains all forces, all particles, all phenomena. If such an equation exists, it would be the modern version of Plato's world of eternal truths, timeless, universal, and unchanging. It would not describe reality, it would be reality. This is what makes Plato's vision so hauntingly relevant. He saw thousands of years ago what physicists are still grappling with today, that perhaps the most real thing is not what we can touch, but what we can calculate. When you walk outside and feel the wind, you think you are encountering matter, sensation, experience, but according to the Platonic view, you are encountering math wearing a mask. The formulas of air pressure, the geometry of motion, the hidden ratios of molecules, these are the true essence. The experience is secondary, the numbers primary. And yet, Plato also hinted that our minds might, in some mysterious way, be attuned to this deeper order. Why else would human beings, fragile animals on a tiny planet, be able to grasp abstract mathematics at all? Why should our brains be capable of holding infinite numbers, complex geometries, and timeless proofs? Perhaps it is because we ourselves are part of that mathematical fabric, fragments of the larger equation trying to comprehend itself. Thus, when we talk about Plato's perfect forms in the context of reality as a mathematical equation, we are not simply revisiting an old philosophy. We are touching the roots of an idea that refuses to die, the suspicion that what we call reality is not ultimate, but derivative, that numbers, not matter, are eternal, and that to study mathematics is not just to learn, it is to awaken to the truth that reality might be nothing more than an equation, written in a language older than time. When you step outside and look at the natural world, it appears chaotic at first glance. The swirl of leaves in the wind, the jagged cliffs of mountains, the veins of a leaf or the spiral of a seashell, all of it seems too irregular to be reduced to anything as rigid as numbers. And yet, the closer you look, the more undeniable it becomes. Nature is not random, it is filled with ratios, proportions, and patterns that repeat themselves across scales. Hidden beneath the surface of apparent disorder lies mathematics, humming like a secret rhythm of existence. Perhaps the most famous example of this is the golden ratio, often denoted by the Greek letter phi, roughly equal to 1.618, comma. This ratio appears again and again in natural structures. The spiral of galaxies, the pattern of sunflower seeds, the arrangement of leaves on stems, the shells of mollusks. When measured, these shapes echo the golden ratio with uncanny precision. Architects and artists through history have mimicked this pattern in their works, believing it to embody a universal standard of beauty. But nature did not copy humans. Humans copied nature. The universe itself seems to be built upon this mathematical proportion. Then there is the Fibonacci sequence, a simple progression of numbers, 1, 1, 2, 3, 5, 8, 13, where each number is the sum of the two before it. At first, this might appear as a quaint curiosity, but look again at the world around you. Petals on a flower often follow Fibonacci numbers. Pine cones and pineapples grow with spirals that match the sequence. Even hurricanes, tornadoes, and the spiraling arms of galaxies exhibit Fibonacci patterns when plotted. This is no accident. It suggests that the laws governing growth, distribution, and balance in the universe follow mathematical logic. The messy beauty of nature hides equations at its core. Consider the honeybee colony, one of the oldest symbols of cooperation in nature. The family tree of male and female bees follows Fibonacci ratios. Male bees have one parent, a queen, while females have two, a queen and a drone. The structure of ancestry produces patterns that reflect the Fibonacci sequence directly. The buzzing hive, with all its apparent chaos, is actually an expression of mathematics in motion. Each wing beat, each hexagonal honeycomb cell, each ratio of inheritance, all of it is governed by numbers. Speaking of honeycombs, why are they hexagonal? A hexagon is the most efficient shape for dividing a surface into equal parts, with minimal waste of space. Mathematically, it provides maximum strength with minimum material. The bees, without ever studying geometry, naturally construct their homes according to principles of efficiency and optimization that humans only later discovered through mathematics. Did bees invent geometry, or are they simply obeying deeper mathematical laws woven into the fabric of life itself? The hidden ratios extend far beyond biology. Crystals, for instance, form with striking mathematical symmetry. Snowflakes, no matter how unique, always reflect six-fold symmetry. Their branches grow in accordance with the same molecular geometry, producing fractal-like designs that astonish with their complexity. Volcanoes and basalt columns form hexagonal pillars as molten rock cools, another sign that geometry dictates even the movements of Earth itself. Everywhere you look, the natural world whispers its equations. One of the most mysterious appearances of hidden mathematics is in the spiral galaxies of the cosmos. Across millions of light years, stars cluster in spiraling arms that follow logarithmic patterns, the very same mathematics found in the spiral of a nautilus shell or the unfolding of a fern. This mirroring across scales suggests something profound. The same mathematical structures govern the smallest patterns of life and the grandest architecture of the universe. It is as if the cosmos itself were composed of recurring equations that echo infinitely. But why should this be the case? If reality were truly random, why would spirals, ratios, and sequences appear across such different domains? Why should a sunflower's seed pattern mirror the shape of galaxies, unless perhaps what we are witnessing is the same equation being solved again and again, on different scales and in different contexts? Just as the same formula can describe sound waves, light waves, and water waves, perhaps reality itself is one grand equation expressing itself in infinite forms. For centuries, scientists have wrestled with whether mathematics is invented or discovered. When we see Fibonacci spirals in flowers, are we imposing numbers on them, or are the numbers already there? The recurrence across domains suggests the latter. Mathematics is not merely our invention, but the underlying structure reality follows. When we describe nature with equations, we are not fabricating a language, we are uncovering one. This insight forces us to reconsider what reality is. Perhaps when you walk through a forest, you are not just seeing plants, insects, and birds. You are moving through an unfolding tapestry of ratios, spirals, and symmetries, a grand living equation. The beauty of a flower, the balance of a shell, the grace of a snowflake. These are not mere accidents of biology or chemistry. They are mathematics revealed through form. And here lies the paradox. We often think of mathematics as cold, abstract, and lifeless. Yet in truth, it is mathematics that gives life its beauty, its growth, its order. The hidden ratios of nature, a proof that reality itself may be nothing more than an equation, endlessly solving itself, endlessly producing the spirals, symmetries, and proportions that make up everything we know. When you stand in awe of a sunset, a storm, or a field of flowers, you are witnessing not chaos, but numbers, written into the fabric of reality. When Galileo Galilei peered through his telescope in the early 1600s, he wasn't just looking at the night sky, he was looking into the very structure of reality. For centuries, humans had gazed at the heavens with awe, but Galileo brought with him a new conviction that the universe was not a story written in myths or scriptures, but a vast book written in mathematics. His famous statement, "The book of nature is written in the language of mathematics," was more than a philosophical musing. It was a revolution in how we see existence itself. To Galileo, mathematics was not simply a tool for describing phenomena. It was the true grammar of reality. The shapes of planets' orbits, the fall of objects to the Earth, the curves traced by projectiles, all these, he argued, were not accidents but could be explained with equations. If you knew the math, you could decode the universe. This was a daring claim in a time when explanations were often sought in theology or tradition. Galileo insisted that numbers, not narratives, governed the cosmos. One of his most striking insights came from his experiments with falling bodies. Before him, Aristotle had taught that heavy objects fall faster than light ones. This truth had been accepted for nearly 2 millennia. Galileo, however, put it to the test. By rolling balls down inclined planes, he discovered that the acceleration of falling objects was uniform, independent of their weight. In other words, nature followed a precise mathematical law, not a philosophical assumption. The idea that something as fundamental as gravity could be measured, predicted, and calculated marked a turning point in human thought. It suggested that the universe could be known not through authority, but through mathematics. Galileo's conviction extended to the heavens. When he turned his telescope to the moon, he saw craters and mountains, not a perfect celestial sphere. When he observed Jupiter, he saw moons orbiting it, shattering the belief that everything revolved around Earth. These discoveries were shocking, but what was even more revolutionary was how he interpreted them, not as curiosities, but as mathematical phenomena. The motions of planets, moons, and stars were not arbitrary. They were governed by measurable, calculable principles. The universe was not chaos. It was a mechanism obeying hidden equations. And yet, Galileo's insistence on a mathematical universe came at great personal cost. His support of heliocentrism, the idea that Earth orbited the Sun, brought him into direct conflict with the Church. To the authorities, the heavens were a realm of divine perfection, not subject to earthly numbers. But to Galileo, the elegance of mathematics was itself a kind of divinity. By decoding the universe through equations, he believed he was uncovering God's true design. In this way, mathematics became not just a scientific method, but a spiritual pursuit. Think about how radical this was. Galileo shifted the center of truth from tradition to numbers, from scripture to experiment, from authority to calculation. He made mathematics the final judge of what was real. No longer could one claim, "It must be so because it has always been said so." The new answer had to be, "Show me the numbers." In doing this, Galileo did more than establish the foundations of physics. He helped redefine reality itself as a mathematical structure. What makes Galileo's perspective especially fascinating is how timeless it feels. Even today, physics relies on his conviction that to understand the universe is to find the right equations. Every modern theory, from quantum mechanics to relativity, echoes Galileo's faith that reality can be written in mathematics. He could not have foreseen Einstein's curved spacetime or Schrödinger's wave functions, but his philosophy anticipated them. Truth lies in numbers. But there is also a deeper implication. If Galileo was right that the book of nature is written in mathematics, then mathematics is not merely descriptive, it is constitutive. A book is not a set of scribbles on paper, it is meaning encoded in symbols. If the universe is a book of math, then reality itself is the symbols, the equations, the language. What we see, moons, craters, falling apples, are just the stories told by that deeper language. In this sense, Galileo's vision points toward the possibility that existence is nothing more than mathematics unfolding. Consider how this idea reframes our daily lives. When you drop a cup of coffee, you're not just spilling liquid, you're witnessing a physical manifestation of differential equations describing acceleration, velocity, and impact. When you look at a rainbow, you're not merely seeing colors, you're seeing light refracting according to Snell's law. To Galileo, these were not coincidences. They were signs that reality is structured by mathematical necessity. And perhaps this is why Galileo's vision resonates so strongly with modern thinkers who argue for the mathematical universe hypothesis. If mathematics explains so much with such precision, if it anticipates phenomena before we even encounter them, perhaps it is not just a language for describing reality, it is reality. Galileo may not have phrased it that way, but his insistence that numbers were the key to truth laid the groundwork for this modern suspicion. In the end, Galileo's mathematical universe was more than a scientific theory. It was a bold claim about the nature of existence, that what we call reality is nothing more than equations made visible. And while his contemporaries may have seen him as a troublemaker, history remembers him as the man who cracked open the cosmic book and revealed its alphabet, mathematics. Johannes Kepler, a contemporary of Galileo, shared the same deep conviction that the universe was mathematical at its core. But while Galileo looked for equations in falling bodies and telescopes, Kepler sought mathematics in the heavens themselves, and what he found was a harmony that bordered on the divine. For Kepler, the cosmos was not simply mechanical, it was musical. Planets moved like notes in a cosmic symphony, each orbit a rhythm, each ratio a harmony. To him, astronomy and music were not separate fields but two expressions of the same underlying mathematics. Kepler began with a mystery. Astronomers before him had long struggled to explain the precise motions of the planets. Ptolemy had used complicated systems of circles within circles to predict planetary positions, and Copernicus had shifted the perspective by placing the sun at the center, but the orbits still didn't quite fit. Something was off, and Kepler, armed with meticulous data from Tycho Brahe's observations, set out to solve the puzzle. What he discovered changed everything. At first, Kepler believed the planets must move in perfect circles. After all, Plato and the ancients had insisted that the heavens were governed by geometric perfection. But no matter how he adjusted the numbers, the data refused to cooperate. Finally, after years of frustration, he arrived at a startling conclusion. The planets moved not in circles, but in ellipses. This was shocking. It meant that the universe was not bound by human ideals of perfection, but by mathematical truth. The orbit of Mars, once thought irregular, was now revealed to obey a simple geometric law. In one stroke, Kepler had brought order to the heavens. His three famous laws of planetary motion, elliptical orbits, equal areas in equal times, and the square-cube relationship between orbital periods and distances remain cornerstones of astronomy. But to Kepler, these were not just cold equations. They were evidence of a deeper harmony, a cosmic music that could be heard only through mathematics. He wrote of the music of the spheres, an ancient idea that the movements of celestial bodies produced a kind of symphony. While no actual sound filled the void of space, Kepler believed the ratios between planetary motions echoed the same ratios that defined musical intervals. In other words, the universe itself was playing music, and mathematics was the score. This vision of harmony was not merely poetic, it was revolutionary. It suggested that the universe was not random, not chaotic, but deeply ordered in a way that humans could comprehend through mathematics. For Kepler, the fact that numbers could so perfectly describe planetary motion was not a coincidence. It was evidence that the universe itself was built upon mathematical law. In his eyes, God was a mathematician, and creation was a grand equation that sang itself into being. The idea of harmony in the heavens also carried philosophical weight. It implied that beauty, truth, and mathematics were inseparable. The elegance of Kepler's laws was not just practical for predicting planetary motion, it was also beautiful in its simplicity. The universe, he believed, must be both rational and aesthetic, governed by principles that appealed not only to the intellect, but also to the sense of beauty. This marriage of mathematics and aesthetics remains a hallmark of physics today, where scientists often describe elegant equations as beautiful and trust their beauty as a sign of their truth. But Kepler's harmonious heavens also raise a deeper question. Why should the universe be harmonious at all? Why should the planets move in patterns that can be expressed in equations? Why should reality echo the structure of music, an art rooted in ratios and time? Unless, perhaps, the universe is not simply a collection of objects moving in space, but a vast mathematical structure unfolding with perfect rhythm. To hear the music of the spheres is to glimpse reality as mathematics in motion. Think of it this way: when you listen to a symphony, you hear instruments blending in harmony, but underneath it all lies mathematics. Frequencies, ratios, vibrations. The beauty of the music comes from its adherence to mathematical patterns. Kepler saw the universe in the same way. The beauty of the cosmos, its balance and order, arose from hidden mathematical laws. We may not literally hear the planets sing, but their movements follow the same logic as melodies. Reality itself might be music, and mathematics, the composer. In modern times, Kepler's insights continue to resonate. Astronomers still use his laws to plot the trajectories of spacecraft, and physicists see in his work the foreshadowing of Newton's universal gravitation. But beyond the practical, his vision offers a profound perspective. The universe is not merely matter in motion, but a harmony of equations. The stars above are not silent after all, they hum with ratios and rhythms that speak the language of mathematics. And perhaps this is why Kepler remained so compelling. He saw what others missed, that the heavens are not just there to be observed, but to be understood as a coherent whole. He believed the universe was intelligible, because it was mathematical. And if that is true, then perhaps our own existence is also part of that harmony. Your heartbeat, your breath, your very thoughts, may be notes in the same grand composition, a mathematical equation expressed as music, playing out across the cosmos. In the end, Kepler's harmonious heavens remind us that reality is not just measurable but meaningful. The universe does not simply exist, it sings, and if mathematics is its language, then reality itself could be nothing more than an eternal song written in numbers, echoing across time and space. If Galileo and Kepler cracked open the book of nature, then Isaac Newton rewrote it in a way that stunned the world. With his Principia Mathematica in 1687, Newton demonstrated that the universe was not a chaotic stage of accidents, but a precise machine governed by mathematical law. He turned the heavens and the earth into a single system, one clockwork mechanism, where every gear, from an apple falling to the orbit of the moon, followed the same timeless equations. For the first time in history, reality itself looked like mathematics in motion. Newton's achievement was staggering. He distilled centuries of observation into 3 elegant laws of motion and the universal law of gravitation. Together these revealed that the same mathematics guiding a cannonball's arc on Earth also described the motion of the planets in the sky. This was more than a discovery. It was a unification. The heavens were no longer divine and separate, and the Earth no longer mundane and distinct. Both were bound by the same mathematical rules, equations woven into the very structure of existence. the metaphor of the clockwork universe arose naturally. Newton's laws portrayed reality as a grand cosmic clock, ticking with perfect precision. Every planet, every stone, every ripple of motion followed the same equations without exception. Given the initial conditions, one could, in principle, calculate the entire future of the cosmos. The idea was intoxicating. Suddenly, human beings were not fumbling in darkness but had the blueprint of reality itself, expressed in the language of mathematics. Newton's equations did more than explain. They predicted. His theory of gravitation allowed scientists to anticipate the return of Halley's comet decades in advance. The movements of tides, the trajectories of planets, the mechanics of machines, all could now be described with mathematical certainty. This predictive power made it seem as though the universe was not just understandable but fully deterministic. In Newton's framework, there was no room for chance. Everything was locked into place by the equations. Reality itself was a machine, and mathematics was the code. This view carried profound philosophical consequences. If the universe is clockwork, where does that leave freedom, randomness, or even mystery? Many Enlightenment thinkers began to argue that humans themselves must also be subject to the same equations. Every decision, every motion of the body, perhaps even every thought, might be the unfolding of physical laws. If you could know the position and velocity of every particle, you could in theory calculate the entire past and future of reality. This chilling possibility, later echoed in the idea of Laplace's demon, suggested that even our sense of choice might be an illusion in a mathematically predetermined world. But the clockwork vision also inspired awe. For Newton, mathematics revealed divine order. He did not see equations as cold abstractions, but as the handwriting of God. The perfection of his laws, the elegance of their application, convinced him that the universe was the deliberate creation of a supreme mathematician. In this sense, mathematics was not just the skeleton of reality, but also its spirit. Newton's faith in equations was inseparable from his faith in a cosmic designer who had wound up the clock and let it run. Over time, Newton's view became the foundation of modern science. From mechanics to engineering to astronomy, the Newtonian framework provided the bedrock for centuries of discovery. Bridges were built, ships navigated, and machines constructed on the assumption that reality is governed by mathematical law. The Industrial Revolution itself can be seen as the unfolding of Newton's insight. If the universe is a machine, then we can build machines that mimic and harness its principles. Yet, even as Newton's laws reigned supreme, cracks eventually began to appear. Subtle discrepancies in planetary motion hinted that his equations, though astonishingly precise, were not the final word. Later, Einstein's theory of relativity and the strange world of quantum mechanics would challenge the clockwork view, revealing that reality might be stranger than Newton imagined. Still, his vision was not erased but expanded. His equations remain accurate in most conditions, a testament to the enduring power of mathematical description. What makes Newton's contribution so critical to our question, whether reality is a mathematical equation, is how fully he revealed the possibility. His laws showed that equations do not merely approximate reality, they govern it. An apple does not fall because of some mystical force, but because the mathematics of gravitation demands it. A planet does not orbit randomly, but because its motion satisfies the equations of motion. The entire universe behaves as though it is solving equations continuously, ticking forward like gears turning in a cosmic clock. Think of reality under Newton's laws as a simulation. Feed in the initial conditions, the mass, velocity, position of every particle, and the universe evolves step by step according to the equations. That is precisely how modern physics engines in video games work. They apply Newton's mathematics to create realistic motion. The uncanny accuracy of those simulations is a reminder that reality itself might be running on similar mathematical principles. Perhaps we do not just describe the world with Newton's equations. Perhaps the world is Newton's equations. The clockwork metaphor may not capture the quantum strangeness or the relativistic bending of space-time, but it revealed something undeniable. Reality can be reduced to numbers. The motions of the cosmos are not wild, unknowable chaos, but precise, calculable laws. And whether one sees them as divine handwriting, as Newton did, or as impersonal logic, as later physicists did, the implication is the same. Reality at its heart behaves as though it is nothing more than mathematics unfolding in time. If Newton revealed the universe as a clockwork machine, later generations of scientists uncovered something even deeper. The universe is not just lawful, but profoundly symmetrical. Symmetry, at first glance, seems like a matter of aesthetics. The balance of a butterfly's wings, the elegance of a snowflake, the pleasing proportions of a temple. But in physics, symmetry is far more than beauty. It is a fundamental clue that reality itself may be built upon mathematical elegance, where balance and invariance are the scaffolding of existence. In mathematics, symmetry means that something remains unchanged under transformation. Rotate a circle, and it is still a circle. Reflect a square in a mirror, and it remains the same shape. This might sound trivial, but in physics, symmetries explain why certain laws of nature exist at all. For example, the fact that the laws of physics are the same today as they were yesterday, that the universe doesn't randomly change its rules over time, is itself a symmetry called time translation invariance. From this symmetry arises the conservation of energy. In other words, the existence of energy itself is a direct consequence of mathematical symmetry. The physicist Emmy Noether made this breathtaking connection explicit in the early 20th century. Her theorem demonstrated that every conservation law in physics, energy, momentum, angular momentum, is born from an underlying symmetry. The fact that momentum is conserved, for instance, comes from the symmetry of space. The laws of physics don't change depending on where you are. If you throw a ball in New York or Tokyo, the same equations apply. The universe is fair, consistent, symmetrical, and this fairness is mathematical in nature. Symmetry is not just a philosophical flourish, it is the foundation of modern physics. Einstein's theory of relativity, for example, is built on the symmetry of space-time. The strange transformations of time dilation and length contraction are not arbitrary quirks, but consequences of preserving the speed of light under different frames of reference. Similarly, the Standard Model of particle physics, our best current theory of fundamental particles, is essentially a grand exercise in symmetry. Quarks, leptons, photons, gluons, their interactions are dictated by mathematical symmetries called gauge groups. Without these symmetries, the universe would not have structure, stability, or order. Reality is not just described by symmetry, it is symmetry expressed through equations. Even in the natural world, symmetry reveals itself as the silent architect. Snowflakes crystallize into hexagonal patterns because of the symmetry in water molecules. Crystals themselves form with regular geometric lattices, echoing the underlying atomic structure. Flowers often grow with radial symmetry, seashells spiral with logarithmic precision, and galaxies stretch their arms in near-mirror balance. When symmetry is broken, beauty still emerges. The slight asymmetry of a human face, for example, creates individuality, but the overall bilateral symmetry gives it coherence. The interplay of symmetry and asymmetry creates the world as we know it, all governed by mathematics. But what does symmetry tell us about the nature of reality? For one, it suggests that the laws of the universe are not arbitrary. They are deeply constrained by mathematical balance. If reality were merely a collection of random happenings, why would conservation laws exist at all? Why would physics be consistent across space and time? The fact that reality obeys symmetries hints that it is fundamentally mathematical, unfolding with the logic of invariance. There is also a haunting implication. If symmetries generate the laws of nature, then perhaps the universe itself exists because it is the simplest, most symmetrical solution to a mathematical equation. Some physicists speculate that among all possible realities, the one we inhabit is the one that balances elegance and stability through symmetry. Our existence, then, is not an accident but the product of mathematics seeking equilibrium. We live in a symmetrical equation, expressed as stars, galaxies, and life. Modern discoveries continue to highlight symmetry's central role. The Higgs boson, famously confirmed in 2012, exists because of symmetry breaking in particle physics. Without this mechanism, particles would not have mass, and the universe would not exist as we know it. Symmetry gives rise to stability, but its breaking gives rise to diversity. This dance between symmetry and asymmetry is itself an equation, a formula that explains why something exists instead of nothing. Think also of the aesthetic side. Scientists often describe mathematical theories as beautiful, and what they mean, consciously or not, is symmetry. Equations that are symmetrical tend to be more elegant, more predictive, more likely to reveal deep truths about the universe. This strange connection between beauty and truth is not coincidence. It may be that beauty itself is simply our recognition of symmetry, our instinctive awareness that the universe is mathematical at its core. What makes symmetry especially fascinating is how it operates invisibly. You cannot always see it directly, but its consequences shape everything. A spinning top maintains its balance because of rotational symmetry. The orbit of planets persists because angular momentum is conserved. Even your own survival depends on symmetry. The biochemical processes in your body follow symmetrical principles. From the DNA double helix to the binding of molecules in cells, you are in essence a pattern of symmetries held together by equations. So when we speak of reality as a mathematical equation, symmetry is perhaps the clearest evidence. It shows us that laws of nature are not arbitrary, but follow the logic of invariance. It reveals why energy, momentum, and mass behave as they do. It explains why the universe is coherent and not chaos. And it whispers something even deeper, that reality itself may be the most elegant solution to a symmetrical equation. The stars above and the atoms within you are not just things. They are balances, ratios, invariances. They are symmetry made visible. In this sense, symmetry is more than beauty. It is existence. And it suggests that the universe itself is not just described by mathematics, but is mathematics, expressed in its most balanced and harmonious form. If there is one field that makes the case most powerfully, that reality is mathematical. It is physics. From its beginnings, physics has been an attempt to strip away appearances and uncover the hidden equations beneath. Unlike poetry or storytelling, which rely on metaphor and interpretation, physics speaks a language of numbers, units, and symbols. And yet, this cold mathematical grammar has an uncanny ability to reveal not just how the world works, but what the world is. When physicists say the laws of physics, they are not describing rules imposed from the outside, they are describing the mathematical structure of reality itself. Physics is unique because it doesn't just use mathematics as a convenient shorthand. Mathematics is woven into its very core. Think about how physical laws are expressed. F equals sine ma, E equals sine ma. Schrödinger's equation, Maxwell's equations. Each of these is not a sentence in English, not a metaphor, but a compact mathematical statement that governs how reality behaves. When we say force equals mass times acceleration, we're not making a poetic observation, we're declaring that the unfolding of motion is itself mathematical. What is even stranger is how universal these equations are. A mathematical law discovered in one context often turns out to apply in a completely different domain. Newton's laws describe apples falling to Earth and planets orbiting the Sun with the same precision. Maxwell's equations describe both the electricity that powers your phone and the light from distant galaxies. Schrödinger's wave equation describes the behavior of electrons in atoms and the probabilities of particles across the entire universe. The language of physics is mathematics, and reality answers to it everywhere, without exception. This universality raises a profound question. Why should math be so effective? Why should the same equation describe phenomena that appear unrelated? The physicist Eugene Winger famously called this the unreasonable effectiveness of mathematics. It is almost as if the universe is written in a single consistent code, and every time we discover a new equation, we uncover another chapter of the same book. If reality were not mathematical, such consistent effectiveness would be miraculous. But if reality is mathematics, then it makes perfect sense. Another striking feature of the mathematical language of physics is its predictive power. Mathematics doesn't just describe what we already know, it reveals what we haven't yet seen. Einstein's equations predicted the bending of light by gravity before it was ever observed. Quantum theory predicted antimatter before it was found in experiments. Maxwell's equations hinted at radio waves decades before anyone built a radio. In case after case, mathematics seems to know reality better than we do, suggesting that the math is not an invention, but the underlying structure of existence. We do not impose equations on the world, we discover them. Consider also the strange fact that when physicists search for deeper theories, they look not only for accuracy but for beauty. They want equations that are simple, elegant, and symmetrical. This reliance on aesthetics might sound unscientific, yet time and again it has worked. The search for beauty led Einstein to relativity and Dirac to predict antimatter. It is as if reality prefers elegance, as if the universe itself is a mathematical equation striving toward simplicity. Beauty, then, may not just be a human preference, but a clue that reality is mathematics manifest. But the language of physics also reveals something unsettling, the gap between our everyday experience and the equations that describe it. The world feels solid, continuous, intuitive, yet the mathematics of quantum mechanics reveals a realm of probabilities, wave functions, and discrete packets of energy. The mathematics of relativity reveals space and time bending, warping, and flowing in ways that defy intuition. Our senses tell us one story, but the mathematics tells another, and the math always wins. When reality and experience disagree, the equations decide what is real. This suggests that what we perceive as reality is, in some sense, an interpretation, a translation of mathematics into sensation. When you touch a table, you feel solidity, but the equations describe electromagnetic forces between atoms. When you see color, you perceive richness, but the math says it is wavelengths of light. What you experience is not the thing itself, but the shadow of the mathematical structure underneath. In this way, physics shows us that reality is not what it seems. It is numbers, ratios, and equations translated into human experience. Perhaps the most astonishing aspect of the language of physics is that it allows us to peer beyond our immediate world into realms we cannot touch. Mathematics lets us describe black holes, quasars, quantum fields, and even the earliest moments of the universe itself. Through equations, we can travel to places our senses could never reach. This ability is not magic, it is the natural outcome of reality being mathematical. If existence were not structured mathematically, our equations would fail at the edges. Instead, they keep guiding us deeper into the unknown. So what does all this mean? It means that physics is not just one discipline among others, but the clearest expression of the idea that reality is mathematics. The universe does not merely obey mathematical laws, as though they were rules imposed from the outside. It is those laws, the atoms in your body, the orbit of the moon, the light from a distant star, all are the unfolding of equations. The language of physics is not a description, it is the reality itself. In the end, when we say the language of physics is mathematics, we are saying something more radical. Reality itself is mathematical. The equations are not symbols we created, they are the architecture of existence. Physics, then, is not the study of matter and energy, but the study of mathematics playing itself out. And perhaps that is why the universe seems so eerily comprehensible, because at its heart it is numbers, not things. One of the most mysterious and powerful aspects of mathematics is its ability to reveal realities that have not yet been observed. Time and again, equations have predicted the existence of phenomena long before human beings confirmed them. This strange foresight suggests something extraordinary. Mathematics does not merely describe reality after the fact, it creates the map of what reality must be, and when the world eventually catches up, it proves the equations were right all along. If this is so, then perhaps reality is not just written in mathematical language, but is itself the unfolding of mathematical predictions. Consider the story of Neptune's discovery. In the early 1800s, astronomers noticed something odd. Uranus wasn't moving exactly as Newton's laws predicted. Instead of discarding Newton's equations, scientists assumed the math was right, and that an unseen planet must be tugging on Uranus with its gravity. By working backwards through the equations, Urbain Le Verrier and John Couch Adams independently predicted the location of this hidden planet. When astronomers pointed their telescopes at the predicted spot, there it was, Neptune revealed by mathematics before the eye ever saw it. Numbers had literally summoned a planet into human awareness. The same thing happened with Einstein's general theory of relativity. His equations implied that light should bend around massive objects because space-time itself curves. At the time, this seemed outlandish. Light had always been considered straight and untouchable. Yet in 1919, during a solar eclipse, astronomers measured starlight bending around the sun exactly as Einstein's math predicted. The equations had seen the truth decades before human instruments confirmed it. Once again, reality was following mathematics like a script. Perhaps the most striking example is the prediction of antimatter. In 1928, Paul Dirac was working on an equation to merge quantum mechanics with special relativity. His math produced an unexpected result. It suggested that every particle must have a mirror twin, identical in mass but opposite in charge. At the time, this sounded absurd. No one had ever seen such things. Yet in 1932, the positron, the first antimatter particle, was detected in a cloud chamber. Dirac had not invented antimatter. The equations had demanded its existence. Reality had no choice but to comply. Over and over, mathematics has behaved like a prophetic oracle. The Higgs boson, often dubbed the God particle, was mathematically required for the standard model of particle physics to make sense. For decades, scientists searched for it, guided only by the math, until it was finally discovered at CERN in 2012. Gravitational waves, too, were first predicted in Einstein's equations, a century before they were finally detected in 2015. Again and again, mathematics writes reality in advance, and the universe obliges. But why should this be so? If mathematics were simply a human invention, a clever way of describing what we see, then equations should not be able to predict things we have not yet observed. They might help us organize knowledge, but they should not create knowledge. And yet, mathematics constantly does. This suggests that the math is not our language imposed on the world. It is the world itself. The universe is a mathematical structure, and when we manipulate equations, we are peering into parts of reality that already exist, waiting to be uncovered. Think about what this implies. When Dirac wrote his equation, he was not inventing antimatter. He was uncovering a corner of reality that had been there all along, hidden until human beings stumbled upon it through math. When Newton's laws hinted at Neptune, they were not fabricating a planet. They were revealing the inevitable consequence of a mathematical structure that governs motion. The math is not describing reality after the fact. It is dictating what reality must be. This predictive power gives mathematics a strange authority. In a way, it means the equations are more real than our senses. Our eyes might tell us that light travels straight, but the math insists it bends in gravity. Our telescopes might miss a planet, but the math insists it must exist. Again and again, the senses are corrected by numbers. Reality, it seems, trusts mathematics more than perception, and so should we. There is also something almost unsettling about this. If equations can predict things we have not yet seen, then perhaps there are entire realms of reality waiting in the mathematics as yet undiscovered. There may be particles, dimensions, or phenomena already written into the equations we have not fully solved. To study mathematics, then, is not simply to describe the present, but to open doors to possible futures. The math already contains them, we just have to follow where it leads. This is why some physicists argue that mathematics is not just a tool but the true essence of existence. The universe behaves as if it is solving equations continuously, unfolding outcomes that were already implicit in the math. From planets to particles, from waves to galaxies, reality manifests what mathematics demands. In this sense, mathematics is not just predictive, it is prescriptive. It tells reality what must exist. Imagine, then, what it means for you and me. If equations predict planets and particles, might they also predict consciousness, life, or even the future of civilization? Perhaps our own existence is already written in the mathematics of reality, waiting to unfold as inevitably as Neptune's orbit or Einstein's bending light. We are not inventing our future. We are enacting equations written into the fabric of existence. In the end, the predictive power of mathematics is perhaps the strongest evidence that reality is itself mathematical. Equations do not merely describe what exists. They reveal what must exist. When reality and math disagree, reality eventually falls in line. And so we must ask, are we living in a world of matter and chance, or are we living inside an equation that already knows what comes next? If Newton revealed the universe as a clockwork mechanism, then Einstein showed us that the clock was far stranger and more beautiful than anyone had imagined. With his theories of relativity, Einstein rewrote the very concepts of space, time, and gravity, and he did so not with metaphors or stories, but with equations of striking elegance. His work is perhaps the most powerful demonstration that reality does not just follow mathematics, it is mathematics. Einstein's most famous contribution, special relativity, began with two deceptively simple postulates. The laws of physics are the same for all observers in uniform motion, and the speed of light is constant for everyone, no matter how fast they are moving. From these assumptions came a cascade of mathematical consequences. Time dilates, lengths contract, and simultaneity becomes relative. Equations, not common sense, dictated these truths. The universe does not behave the way it feels to us. It behaves the way the math requires. This culminated in the most iconic equation in science, E equals sin mess world. This compact statement revealed that mass and energy are not separate things, but two sides of the same mathematical coin. A kilogram of matter contains a staggering amount of energy, equivalent to billions of joules. This was not philosophical speculation, but a hard mathematical truth, one that later powered nuclear energy, both creative and destructive. Once again, mathematics was not describing reality after the fact. It was unveiling reality at its deepest level. But Einstein's true masterpiece was general relativity. Here, he dared to redefine gravity itself. For centuries, gravity had been seen as an invisible force pulling objects together. Einstein instead described it as the curvature of space-time, expressed in his famous field equations. Written compactly, they read, "To the untrained eye, it may look like abstract symbols, but to physicists, this equation is poetry. On the left-hand side is the geometry of space-time, how it bends, twists, and curves. On the right-hand side is matter and energy, the contents of the universe. The equation states simply, matter tells space-time how to curve, and curved space-time tells matter how to move. Reality, in Einstein's view, is not particles floating in empty space, but the dynamic interplay of energy and geometry, written in the grammar of mathematics. What makes these equations remarkable is not only their explanatory power, but their elegance. They are minimal, symmetrical, and deeply beautiful, qualities physicists often use to judge whether a theory is likely to be true. Einstein himself trusted beauty as a guide, convinced that the universe must obey elegant mathematics. Time and again this instinct proved right. His field equations predicted phenomena no one had yet observed, the bending of starlight by gravity, the expansion of the universe, the existence of black holes, and even gravitational waves. Decades later, every one of these predictions was confirmed. The math had known reality before we did. Einstein's work shows us something profound. Mathematics does not merely accompany physics. It is physics. When he reimagined gravity, he did not do it by analogy or intuition. He did it by finding the equation that fit both elegance and consistency. Once written, the math dictated consequences, some of which were shocking even to him. In this way, mathematics seems less like a human tool, and more like a window into a pre-existing structure of reality. But Einstein also raised new questions. Why should the universe obey such elegant equations? Why should geometry and matter be tied together so perfectly? Why should a small set of symbols on paper correspond exactly to the behavior of stars, galaxies, and black holes? The success of Einstein's mathematics suggests that the universe is not random at all, but profoundly ordered in a mathematical way. If reality were not mathematical, we would expect messy approximations, not exact predictions. Yet, Einstein's equations describe the universe with uncanny precision. This is why many physicists today echo Einstein's conviction that mathematics is woven into the fabric of existence. His field equations do not merely describe how things move, they reveal what space and time actually are. They show that reality itself has a mathematical geometry, and that what we call gravity is not a force but an equation expressed in space-time. To say reality is an equation is not metaphorical here, it is literal. There is also a haunting beauty in Einstein's vision. His equations suggest that the universe is not chaotic, but harmonious, not arbitrary but inevitable. Space bends, time slows, light curves, all because the math demands it. We may feel like free observers in a vast cosmos, but in truth, we are participants in an equation that unfolds with every moment. Our very existence, our weight, our motion, our place in time, is dictated by the geometry written in Einstein's symbols. And yet, Einstein himself was never fully satisfied. He spent his later years searching for an even deeper set of equations, a unified field theory that would bring together gravity and electromagnetism under one mathematical umbrella. Though he did not succeed, his quest revealed something important, the conviction that beneath the apparent complexity of the universe lies a single, elegant equation. Reality for Einstein was not just governed by math, it was math waiting to be unified. In the end, Einstein's elegant equations transformed our view of reality. They revealed that space and time are not backdrops but dynamic players, that matter and energy are interchangeable, and that the universe itself is a living geometry. More importantly, they showed us that mathematics is not a tool we impose on the world, it is the world, and if equations can reshape our understanding of gravity, space and time, then perhaps all of reality is nothing more than mathematics unfolding in its most beautiful form. If Einstein's relativity showed us the vast elegance of the cosmos, then quantum mechanics revealed the bizarre mathematical foundations of the microscopic world. And unlike relativity, which still appeals to our sense of geometry and curvature, quantum mechanics defies intuition entirely. At its heart it is a mathematical framework, an abstract set of equations that describe probabilities rather than certainties, wave functions instead of solid particles. What makes it extraordinary is that while it feels incomprehensible to human common sense, the mathematics works with almost supernatural precision. Quantum mechanics might be the clearest example yet that reality itself is mathematics unveiled. The story begins with the discovery that energy is not continuous, but quantized. Max Planck introduced the idea that light could only be emitted in discrete packets, quanta, to solve problems in black body radiation. This radical proposal implied that at the deepest level, Nature does not flow smoothly but clicks along like a mathematical grid. Later, Albert Einstein explained the photoelectric effect using the same principle, showing that light behaved not just as a wave, but also as particles called photons. From the very start, quantum theory forced us to abandon intuitive pictures and embrace mathematics as the only reliable guide. The cornerstone of this strange new world is the Schrödinger equation, a differential equation that governs how quantum states evolve over time. Instead of telling us exactly where a particle is, it provides a wave function, a mathematical object that encodes the probabilities of finding the particle in different places. This is not an approximation or a flaw in our measurements. It is reality itself behaving probabilistically. In other words, at the quantum level, existence is not a collection of tiny billiard balls, but a mathematical probability field. Only when we measure does the wave function collapse into a definite state, and even then, the collapse is dictated by the probabilities encoded in the equation. What makes this more astonishing is the accuracy of the mathematics. Quantum electrodynamics, the theory describing interactions between light and matter, makes predictions that match experiments to 12 decimal places. No human-made system achieves such precision. If reality were not mathematical at its core, how could equations possibly align with experiments so flawlessly? It is as if the universe is not just compatible with mathematics, but is mathematics running on an infinite scale. Quantum mathematics also reveals phenomena that defy classical logic. Superposition allows particles to exist in multiple states at once until observed. Entanglement connects particles across vast distances so that the state of one instantly determines the state of another, regardless of separation. Einstein himself called this spooky action at a distance, but experiments repeatedly confirm it. These are not metaphors. They are mathematical truths. The equations demand them, and reality complies. Once again, math dictates what is real, not our intuition. Perhaps the most unsettling implication of quantum theory is the role of the observer. In classical physics, objects exist independently of us. In quantum mechanics, the act of measurement collapses possibilities into outcomes. This does not mean consciousness creates reality in a mystical sense, but it does mean that reality is not independent of interaction. The mathematics tells us that what exists is a probability field, and only through measurement does it manifest as an event. Reality, then, is not solid but relational, and the rules of that relation are written in equations. Quantum mechanics has also forced physicists to reconsider the meaning of matter itself. Particles, once thought to be fundamental, are now seen as excitations of underlying quantum fields. These fields, described entirely through mathematics, pervade the universe. What we call an electron is just a ripple in the electron field. What we call a photon is a ripple in the electromagnetic field. Reality at its foundation is not objects, but equations describing the behavior of fields. Matter is math in motion. And quantum mathematics continues to predict realities we have yet to fully comprehend. The standard model of particle physics is essentially a vast equation describing how fundamental particles interact. Every confirmed discovery, from the Higgs boson to neutrino oscillations, has flowed from this framework. Yet the model is not complete. It does not include gravity, nor does it explain dark matter or dark energy. Still, it demonstrates the same haunting truth. Mathematics knows more than we do. The equations already contain the answers, waiting for us to uncover them. The strangeness of quantum mechanics often leads people to dismiss it as abstract or unreal. Yet without it, our modern world would not exist. Computers, smartphones, lasers, medical imaging, GPS, all depend on quantum principles. Every time you swipe on a screen or send a text, you are living inside quantum mathematics at work. The bizarre equations are not distant abstractions. They are the reality you inhabit every day. So what does all this mean for the idea that reality is a mathematical equation? It means that at the smallest scales, where intuition fails, mathematics is not just helpful, it is the only thing that works. Quantum mechanics does not allow us to imagine particles as little dots bouncing around. Instead, it forces us to accept that reality is a probability field, a wave function, an equation evolving over time. What is real is not the particle itself, but the math that governs it. Perhaps then, the quantum world is not strange at all. Perhaps it is simply the clearest glimpse of reality's true nature. Mathematics, unmasked. When we see a particle behave like a wave, when we see two entangled particles act as one across light years, when we calculate probabilities instead of certainties, We are seeing the mathematics that reality really is. The universe, at its most fundamental level, is not matter, not energy, but equations unfolding in time. At first glance, chaos seems like the enemy of mathematics. Where equations bring clarity and predictability, chaos looks random, wild, and incomprehensible. A hurricane twisting unpredictably across the ocean, a dripping faucet switching erratically from steady to sporadic, the turbulence of air rushing over a wing, all of these look like pure disorder. Yet, the great revelation of the late 20th century was that even chaos contains hidden order. Beneath apparent randomness lies a structure that can only be revealed through mathematics. In other words, even chaos speaks in numbers. The foundation of chaos theory is the recognition that many systems in nature are deterministic but unpredictable. That is, their behavior is governed by precise equations, yet small differences in starting conditions lead to wildly different outcomes. This sensitivity, often called the butterfly effect, means that the flap of a butterfly's wings in Brazil could set off a chain of atmospheric events that eventually causes a tornado in Texas. The system is not random, it is mathematical, but the outcomes are so sensitive that prediction becomes nearly impossible. The equations that govern chaotic systems are surprisingly simple. Take the logistic map, a basic mathematical formula that models population growth. At low growth rates, it produces stable populations. At higher rates, it oscillates between two values, then 4, then 8. Push it further, and the system becomes chaotic, never repeating yet, never truly random. When graphed, the logistic map reveals intricate patterns, windows of stability nestled within turbulence. From simplicity emerges complexity, and from complexity emerges beauty. What looks chaotic hides a deep mathematical structure. Perhaps the most iconic symbol of chaos theory is the fractal, a geometric shape that repeats itself at different scales. The Mandelbrot set, generated by a simple equation, produces infinitely complex, self-similar patterns. Zoom in on any edge, and you find smaller versions of the whole, endlessly repeating. Nature echoes this fractal logic everywhere, in the branching of trees, the veins of leaves, the shape of coastlines, the structure of lungs, and the distribution of galaxies. What appears irregular to the eye is in truth fractal order written in mathematical code. This discovery carries profound implications for our understanding of reality. If even chaos is governed by equations, then randomness itself is an illusion. The storm that destroys a coastline, the turbulence that makes flight bumpy, the fluctuations of the stock market, all are expressions of deterministic equations unfolding in complex ways. The unpredictability lies not in the absence of order, but in the overwhelming sensitivity of the system. Reality may feel chaotic, but at its foundation, it is still mathematics. Chaos theory also shows how boundaries between order and disorder are not fixed but dynamic. Systems shift between stability and chaos in ways that mirror life itself. A heartbeat, for example, is not perfectly regular. If it were, it would signal illness. Healthy heartbeats contain slight irregularities, a balance between order and chaos that sustains life. Similarly, ecosystems and economies thrive on this balance. Too much order and they stagnate. Too much chaos and they collapse. Once again, the mathematics reveals that existence itself thrives on the interplay of structure and unpredictability. But there is a deeper philosophical lesson here. Chaos theory suggests that complexity, beauty, and life emerge not in spite of mathematics but because of it. The fractal branching of trees allows them to maximize sunlight. The chaotic swirls of blood flow ensure efficient circulation. The jagged coastline increases ecological diversity. What looks like disorder is often a more advanced form of order, one we cannot perceive without equations. Mathematics is not only behind symmetry and stability, but also behind turbulence, irregularity, and change. Consider also the haunting possibility that chaos makes free will feel real. If deterministic equations can produce unpredictability, then perhaps what we experience as choice or chance is the result of chaotic systems unfolding. Our brains, with their billions of interconnected neurons, are highly sensitive to initial conditions. A single tiny variation in electrical firing could cascade into a completely different outcome. A decision, a memory, a word spoken or withheld. The unpredictability feels like freedom, but beneath it may lie nothing more than mathematics, producing complexity beyond comprehension. Chaos theory also reminds us that human perception is limited. To us, the world looks messy and irregular, but mathematics reveals hidden layers of structure we could not otherwise see. A coastline looks jagged, but measured mathematically, its fractal dimension falls within a precise range. Clouds appear shapeless, yet their geometry follows fractal scaling laws. Even the distribution of earthquakes, forest fires, and financial crashes follows mathematical power laws. What we call chaos is often our inability to perceive the equation clearly. In the end, chaos does not disprove the mathematical nature of reality, it strengthens it. It shows that even the wildest, most uncontrollable aspects of existence are governed by numbers. The fluttering of leaves in the wind, the roaring of waves, the beating of your heart, all of it arises from equations sensitive enough to produce infinite variety. Chaos is not a rejection of mathematics, but its deepest expression, a reminder that equations do not just create order but also complexity, unpredictability, and life itself. So when we ask whether reality could be nothing more than a mathematical equation, chaos theory offers a powerful answer. Even in the places where reality looks least mathematical, in storms, turbulence, and disorder, equations reign. The randomness is only apparent, the order is real, hidden beneath layers of complexity. Chaos too is mathematics, and reality is its canvas. When people think of mathematics, they often imagine cold calculations, rigid logic, and endless rows of symbols. But to mathematicians, mathematics is not only about accuracy, it is about beauty. Nowhere is this beauty clearer than in mathematical proofs. A proof is not just a demonstration that something is true, it is a revelation of why it must be true. And in that why, in that elegance, many see the strongest evidence that mathematics is not a human invention, but the fabric of reality itself. For if truth is beautiful, and mathematics reveals truth, then perhaps reality itself is beauty written in numbers. One of the most famous examples is Euclid's proof of the infinitude of primes. More than 2,000 years ago, Euclid showed that no matter how many prime numbers you find, there will always be more. His proof was breathtaking in its simplicity. Assume you have a complete list of primes, multiply them together, add 1, and the result must either be prime or divisible by a prime not on the list. Instantly, infinity emerges. The argument requires no complex tools, just pure logic. The beauty lies in how inevitable it feels. The conclusion seems to have been waiting for us, timeless and eternal. This elegance is not limited to number theory. The Pythagorean theorem, perhaps the most famous mathematical truth, has hundreds of different proofs, each offering a new perspective on the same eternal relationship. Some use geometry, others algebra, still others clever visual rearrangements. The fact that such different approaches converge on the same result suggests that the truth is not human-made but woven into the structure of reality. Triangles are not cultural artifacts, they exist everywhere, and their properties are true whether humans discover them or not. The beauty of the theorem, and the many ways to prove it, testifies to the universality of mathematics. Mathematicians often speak of proofs in terms of aesthetic criteria: simplicity, elegance, inevitability. A proof that is long and clumsy may still be correct, but it is not beautiful. A beautiful proof feels like the unveiling of something that was always there, hidden beneath the surface. It gives the sense that the universe itself was whispering the answer all along, and we have finally learned to listen. This aesthetic dimension of mathematics, the fact that truth often comes wrapped in beauty, suggests that reality itself may be fundamentally mathematical. Why else would the universe prefer elegance? Consider Euler-Sipp's identity, often called the most beautiful equation in mathematics. In just one line, it unites the 5 most fundamental numbers in mathematics: e, the base of natural logarithms; I, the imaginary unit; p, the ratio of a circle's circumference to its diameter; 1, the multiplicative identity; and 0, the additive identity. Somehow, numbers from algebra, geometry, and analysis converge into a single simple relationship. Many mathematicians describe seeing Euler's identity as a near-spiritual experience, as if the universe had momentarily revealed its secret architecture. This is not beauty as decoration, it is beauty as truth. But why should mathematics be beautiful at all? If it were merely a human invention, designed only for utility, why would it possess elegance? Why would equations not just work, but work in ways that inspire awe? The fact that beauty and truth align so consistently in mathematics suggests that we are not imposing structure, but uncovering it. The beauty of proofs is not ours, it belongs to reality. This connection between beauty and truth is also evident in physics. Time and again, elegant equations turn out to be correct. Einstein's field equations, Maxwell's laws of electromagnetism, Schrödinger's wave equation, All are celebrated not just for accuracy, but for elegance. Physicists often trust beauty as a guide. If a theory feels clumsy, it is suspect. If it feels beautiful, it is likely correct. Why should this be the case, unless the universe itself is mathematical, and beauty is the sign that we are touching its core? There is also a paradox here. A proof reveals that something must be true, but it also shows that it was always true, long before any human wrote it down. The infinitude of primes existed before Euclid. Euclid's identity was valid before Euclid. These truths do not depend on culture, language, or even the existence of humans. They exist outside time, in a realm of necessity. If reality itself is nothing more than a mathematical equation, then proofs are the windows through which we glimpse its eternal nature. And yet, the beauty of proofs also reminds us that mathematics is not sterile but alive. To see a proof unfold is to witness creativity and discovery. Mathematicians often describe the experience of proving something as akin to finding a path through a dense forest, where suddenly the trees part and the destination is clear. The joy, the awe, the sense of inevitability. These are not feelings one expects from abstract symbols, but they arise precisely because mathematics feels like uncovering something real. So when we talk about the beauty of proofs, we are not just admiring clever arguments. We are encountering evidence that reality is fundamentally mathematical. The elegance of proofs hints that truth and beauty are two sides of the same coin, and both are woven into the universe. The fact that mathematics can be both useful and beautiful is no coincidence. It is the signature of a reality that is itself an equation, one that values elegance as much as accuracy. In the end, proofs are more than demonstrations. They are revelations. They remind us that mathematics is not invented but discovered, that beauty and truth are inseparable, and that reality itself might be the grandest proof of all. If we are indeed living inside a mathematical equation, then every proof we uncover is a glimpse of the equation's elegance, fragments of eternal beauty written into the very fabric of existence. One of the most astonishing features of mathematics is its universality. Equations discovered in one field of study somehow apply in completely different and seemingly unrelated domains. A formula describing the motion of planets might also describe the path of a falling apple. Equations for fluid turbulence might also model fluctuations in financial markets. Patterns that emerge in biology can mirror those in physics, and structures in chemistry often echo those in music. The fact that mathematics can leap across domains suggests something extraordinary. It is not just a tool humans apply, but the underlying fabric of reality itself. Take the example of wave equations. Originally developed to understand vibrations in strings and sound, they turned out to describe the behavior of light, water, and even probability waves in quantum mechanics. The same mathematics governs how a violin string hums, how a radio antenna transmits, and how an electron behaves in an atom. What possible connection could exist between music, radio waves, and atomic particles, except that they are all expressions of the same equation? Universality suggests that reality is not a collection of separate phenomena, but one equation unfolding in different forms. Another striking example is the mathematics of exponential growth. Whether you are modeling bacterial populations in a petri dish, the spread of a viral infection, the growth of an investment account, or even the expansion of the universe, the same exponential curve appears. Different contexts, same formula. It is as if the universe prefers certain patterns, reusing the same equations at multiple scales. If mathematics were merely a human invention, why would the same formula apply equally well to microbes, money, and galaxies? Fractals, too, demonstrate this universality. The branching of trees, the veins of leaves, the lightning bolt across the sky, and the structure of river networks all follow fractal mathematics. The same geometry explains blood vessels in your body, and the clustering of galaxies in space. From the microscopic to the cosmic, the same equations repeat. Universality is not coincidence. It is the signature of a reality built upon mathematics, where the same rules apply everywhere. The phenomenon of resonance provides another powerful case. In physics, resonance occurs when a system vibrates at its natural frequency, amplifying energy. A child pumping their legs on a swing, a singer shattering glass with their voice, or electrons in an atom absorbing light, all follow the same mathematics of resonance. Once again, music, mechanics, and atomic physics share the same equation. These shared patterns imply that the underlying structure of reality is mathematical, not merely descriptive. Universality also appears in the statistics of randomness. The mathematics of probability developed to understand dice games and gambling, now underpins weather prediction, quantum physics, genetics, and even artificial intelligence. The same distributions, Gaussian, Poisson, power laws, emerge again and again, across contexts, as different as earthquakes, internet traffic, and neuron firing in the brain. Chaos might look different in each case, but the statistics of uncertainty remain the same. Reality may look diverse on the surface, but underneath, it is one interconnected equation. Perhaps the most striking example of universality lies in Fourier analysis, the decomposition of complex signals into simple waves. Whether analyzing sound, light, heat, or brain activity, Fourier mathematics allows us to break down complexity into simple components. It is the same mathematics that powers your MP3 files, medical imaging, and even the analysis of cosmic microwave background radiation from the early universe. That a single mathematical technique works equally well for music compression and the study of the Big Bang is not coincidence. It is universality, proof that reality is fundamentally mathematical. This universality also extends to human experience. The mathematics of networks describes not only neurons in the brain, but also social interactions, computer systems, and ecosystems. The same formulas that describe how ideas spread in a population can also describe how viruses spread through a community, or how power grids distribute electricity. Different domains, same underlying math. If reality were not fundamentally mathematical, why would the same structures emerge everywhere? Universality also explains why mathematics can act as a bridge between disciplines. A biologist and a physicist might study very different systems, but the equations they use often overlap. This convergence suggests that the universe is not a patchwork of disconnected laws, but a single coherent mathematical structure. We may call it physics, chemistry, biology, or economics, but beneath the surface it is all the same mathematics playing itself out. The universality of mathematics raises an unsettling question. Are there truly separate domains at all, or are we the ones imposing divisions? Perhaps nature does not care whether we call something biology, physics, or sociology. To the universe, they are all solutions of the same underlying equation. Our categories are human inventions, but the mathematics is universal. If so, then what we call reality is simply mathematics manifesting in infinite forms, across every scale and system. This perspective suggests a profound unity to existence. The heartbeat of an infant, the spiral of a galaxy, the oscillations of an atom, the spread of an idea, all are expressions of the same mathematical logic. Reality is not a collection of separate events, but a single equation echoing through countless forms. To understand one domain is, in a sense, to understand them all. That is the power and the mystery of universality. So when we ask whether reality could be nothing more than a mathematical equation, universality across domains provides one of the clearest answers. It shows us that the same mathematics governs sound and light, growth and decay, order and chaos, the living and the non-living, the small and the vast. This is not coincidence. It is reality revealing itself as mathematics, endlessly versatile, endlessly consistent, endlessly universal. Is mathematics something we invent, or something we discover? This question lies at the heart of the debate over whether reality itself is a mathematical equation. If mathematics is merely a human invention, like language or money, then the fact that it works so well in physics might be a lucky coincidence. But if mathematics is a discovery, an eternal truth that exists independent of us, then we are not creating numbers and equations. We are uncovering the very structure of reality itself. Consider the difference. Invention implies arbitrariness. The rules of chess are invented. They could have been otherwise. The English language is invented. We could have used different words. But discoveries like the laws of gravity or the shape of DNA are not arbitrary. They exist whether humans notice them or not. When we talk about the Pythagorean theorem, are we describing a human-made rule or an eternal truth about right triangles that existed before humans ever walked the earth? Most mathematicians lean toward discovery. Prime numbers, for example, are not things we invented. They exist in the sequence of natural numbers, whether or not anyone studies them. The fact that 17 is prime is not a human convention. It is an eternal truth. If intelligent aliens exist, they too would discover prime numbers. They might call them by another name, but the underlying property would be the same. This universality strongly suggests that mathematics is not cultural but fundamental. The predictive power of mathematics strengthens this argument. As we saw with Neptune, antimatter, and gravitational waves, Equations point to realities long before we observe them. If mathematics were an invention, how could it anticipate truths we did not yet know? You cannot invent something, and then be surprised when it reveals new knowledge beyond what you put into it. Discovery makes more sense. We stumble upon equations that already contain truths waiting to be unveiled. But perhaps the most compelling argument for mathematics as discovery is its uncanny objectivity. Different cultures, separated by centuries and geography, often arrive at the same mathematical truths independently. Ancient Babylonians, Greeks, Indians, and Chinese all developed forms of geometry and algebra. They did not borrow from one another in every case, yet they found the same results. This convergence suggests that mathematics is not a human creation, but something woven into the universe itself, waiting to be uncovered by any sufficiently curious mind. Philosophers sometimes frame this in terms of Platonism, the belief that mathematical objects exist in an abstract realm of eternal truths, independent of human thought. Under this view, when we do mathematics, we are not inventing but glimpsing into this realm, discovering structures that were always there. The number pi, for example, is the ratio of a circle's circumference to its diameter, no matter what universe you inhabit. If circles exist, pi will be there. It is not ours. It is reality's. Yet, not everyone agrees. Some argue that mathematics is a human construct, a language we have built to describe patterns. The fact that it works so well might simply mean that we have shaped it to fit the world, like tailoring a suit. But this explanation falters when we remember how often mathematics goes beyond description into prediction. Tailored languages do not discover things outside themselves. Equations do. The discovery perspective also reframes how we see ourselves. If mathematics is eternal, then we, in studying it, are not inventors but explorers of reality's foundation. Each proof, each theorem, each equation is a new land uncovered in a realm that has always existed. In this sense, mathematics is not human at all. It is the universe revealing itself through us. To solve an equation is to translate a fragment of reality's eternal structure into human understanding. Think of it this way. When Newton discovered calculus, he did not create it out of nothing. The relationships between rates of change and areas under curves already existed in the fabric of reality. Newton and Leibniz simply uncovered the rules. When Maxwell wrote his equations of electromagnetism, he was not inventing them. He was revealing the deep mathematical order already governing electricity and magnetism. Each discovery is like brushing dust off an inscription carved into the foundation of existence. There is something almost humbling about this. If mathematics is discovery, then it existed long before us and will exist long after us. Even if humanity vanished tomorrow, the truths of geometry, algebra, and number theory would remain. They are not dependent on culture or biology. They are part of reality itself. In this sense, mathematics is immortal. We are temporary vessels that glimpse eternal truths. And yet, this discovery perspective raises an unsettling thought. If mathematics exists independent of us, then perhaps we ourselves are part of it. Perhaps consciousness, life, and thought are not accidents, but expressions of equations. We are not inventors peering into an external world. We are pieces of the mathematical equation discovering itself. The act of doing mathematics might be the universe becoming aware of its own structure. In the end, whether mathematics is invention or discovery is more than a philosophical puzzle. It is a question about the nature of reality. If invention, then the universe just happens to fit our constructs. If discovery, then the universe is mathematics, and we are decoding its equation. All evidence, the universality, the predictive power, the objectivity points toward discovery. And if that is the case, then reality itself is not physical first and mathematical second. It is mathematical first, with the physical as its shadow. One of the most baffling clues that reality might be nothing more than a mathematical equation lies in the existence of universal constants. These are numbers that appear everywhere in physics, anchoring the structure of reality with uncanny precision. They are not chosen by us, nor do they change with time or place. They simply are. The speed of light in a vacuum, Planck's constant, the gravitational constant, the fine structure constant. These numbers are woven into the fabric of existence. Without them, reality would not just look different, it would not exist at all. Take the speed of light, 299,792,458 meters per second. It is not simply the maximum speed for light, it is the maximum speed for causality itself. Nothing can move faster, no information can travel quicker. This number defines the very geometry of space-time. If it were even slightly different, the entire structure of relativity would collapse, and the universe as we know it could not exist. But why this number? Why not faster, slower, or variable? The mystery lies in the fact that the universe seems calibrated to exact mathematical values, as if written into the code of reality. Then there is Planck's constant, the tiny number that defines the quantum world. It tells us how energy comes in discrete packets, or quanta, rather than continuous flows. Without this constant, atoms would not form, chemistry would not exist, and life would never emerge. It is as though the universe has been quantized with mathematical precision, a strange reminder that even the smallest scales of reality are governed by equations that require exact numbers. Perhaps the most enigmatic is the fine structure constant, alpha, approximately equal to 1/137th. This dimensionless number governs the strength of electromagnetic interactions. Change it even slightly, and the stability of atoms falls apart. Stars would not burn, chemistry would disintegrate, and life would be impossible. The universe, it seems, balances precariously on this mathematical knife's edge. As the physicist Richard Feynman once said, all good theoretical physicists put this number up on their wall and worry about it. It is one of the deepest mysteries, why 1/137th, and not some other value. Where did this precise number come from? The constants do not merely exist in isolation. They interlock like parts of a grand equation. The ratio of the strengths of forces, gravity, electromagnetism, the nuclear forces, determines the architecture of the cosmos. If the gravitational constant were a fraction stronger, stars would collapse into black holes, a fraction weaker, and galaxies would never form. If the nuclear strong force were slightly different, protons and neutrons would not bind, and atoms would not exist. These constants are not arbitrary. They are finely tuned to mathematical perfection. The universe seems to have been programmed with values that make existence possible. This phenomenon has sparked endless debate. Some argue it suggests design, that the constants were chosen deliberately. Others suggest the multiverse theory that countless universes exist with different constants, and we simply live in the one where the math allows life. But both explanations circle the same point. The constants are not negotiable. They are mathematical parameters, etched into reality itself, like numbers hard-coded into an equation. They are not adjustable dials we can turn. They are fundamental truths. If reality is an equation, then these constants are its defining coefficients. Even more puzzling is the fact that some constants might not be truly fundamental, but could emerge from deeper mathematics we have not yet uncovered. For instance, the fine structure constant might be the result of hidden symmetries or undiscovered laws. If this is true, then the constants are not arbitrary at all. They are inevitable consequences of a deeper equation. In this view, we have not reached the end of the math, but are still climbing toward the root formula that generates everything. The constants, then, are clues pointing us to the ultimate equation of reality. This mystery raises a profound question. Do the constants exist because the universe exists? Or does the universe exist because the constants exist? If the latter, then reality is not primary. The numbers are. We live in a cosmos where mathematics dictates the possible, and what we call reality is just the expression of numbers solving themselves across time and space. Think about what this means for daily life. The light you see from the sun, the chemistry in your body, the stability of the ground beneath your feet, all depend on the precise values of a few constants. If they were different by even the tiniest fraction, you would not be here to wonder about them. This is more than coincidence. It is evidence that reality itself is not matter, but mathematics, unfolding with the precision of constants that never waver. To live in such a universe is to live inside an equation so exact that even the smallest deviations would erase existence. Every breath you take, every star that shines, every thought that crosses your mind is permitted, because the numbers allow it. You are not simply a being in a universe, you are a solution to an equation balanced on constants we barely understand. And so, the mystery of constants stands as one of the strongest hints that reality is fundamentally mathematical. The constants are not decorations on the laws of physics. They are the anchors of existence. And until we understand why they are what they are, we remain students of a vast equation that is still revealing its terms. For most of human history, matter seemed like the ultimate reality. Rocks, trees, bodies, stars, all appeared solid, tangible, undeniably real. But the deeper science has probed, the more this solidity has dissolved, revealing something stranger. Matter itself may be an illusion. Atoms, once thought to be indivisible building blocks, are mostly empty space. Particles, once thought to be fundamental, dissolve into wave functions, fields, or vibrations of something deeper. At the bottom, reality does not look like stuff at all. It looks like mathematics. Start with the atom. When you picture it, you may imagine tiny balls orbiting like planets around a nucleus. But in truth, electrons are not little marbles circling in neat paths. They are described by probability distributions, mathematical clouds that tell us where the electron is likely to be found. The atom is not a miniature solar system. It is an equation manifest. The solidity of matter, the feeling of hardness when you press your hand against a table, comes not from objects touching, but from electromagnetic forces between atoms, themselves governed by equations. What you feel is not matter, it is math. Go deeper, still, into the subatomic world. Protons and neutrons, once considered fundamental, are themselves made of quarks, particles that are never observed in isolation, only in groups. Quarks and gluons are not things in the traditional sense. They are excitations of quantum fields. These fields are not material substances, but mathematical structures that permeate the universe. In this picture, the physical dissolves entirely. What we call matter is the outcome of equations describing how fields vibrate, interact, and balance. Even more astonishing is that most of the atom is empty space. The nucleus is tiny compared to the whole atom, and the electrons are smeared out in probability waves. If the nucleus of an atom were the size of a marble, the electrons would be orbiting football fields away, and everything in between would be empty. The table beneath your hand, the ground beneath your feet, your own body, all are mostly void. The sense of solidity is an emergent illusion created by forces, not by matter. At the bottom, it is mathematics describing interactions that creates the illusion of stuff. This illusion deepens with Einstein's revelation that mass and energy are interchangeable. E=mc² tells us that what we call matter is simply a concentrated form of energy. But what is energy? In physics, energy is not a thing, but a number, a quantity that measures the capacity to do work. In other words, matter is nothing more than numbers in a different form. The bedrock of reality is not substance but quantities, not objects but equations. The standard model of particle physics makes this explicit. Every particle is an excitation of a quantum field, and the behavior of these fields is governed entirely by mathematics. When physicists simulate particles on supercomputers, the equations produce results that match experiments with incredible precision. The particle is not separate from the equation. The particle is the equation. Reality in this view is mathematics pretending to be matter. The illusion of matter is also evident in the strange duality of particles and waves. Light behaves as a particle in some experiments, as a wave in others. Electrons do the same. They are neither fully particle nor wave, but mathematical entities that take on different forms depending on context. What we see as matter is just the visible tip of an underlying equation, shifting its appearance based on how we observe it. Even at macroscopic scales, this illusion holds. The solidity of everyday objects is an emergent phenomenon. Your chair does not exist as a chunk of substance, but as a temporary structure stabilized by electromagnetic forces, themselves expressions of mathematical constants. If those constants shifted even slightly, the chair would dissolve, the molecules would disband, and what you call matter would vanish. The illusion of solidity depends entirely on mathematics holding the universe together. Philosophically, this forces us to rethink what it means to exist. If matter is not ultimate, then what is? The evidence suggests it is mathematics. Fields, wave functions, probabilities, and symmetries are not physical objects but mathematical structures. They are what is truly there. The material world in this sense is a shadow, a projection of equations onto our senses. We believe in matter because we can touch and see it, but touch and sight themselves are interpretations of mathematical interactions. Consider the analogy of a video game. On the screen you see characters, landscapes, and objects. They look solid and real, but beneath them lies nothing but code. The code is not visible to the player, but it is the true reality of the game. The characters are illusions generated by mathematical instructions. In the same way, our world of matter may be nothing more than the visible projection of deeper mathematical code. This does not mean the illusion is unimportant. On the contrary, it is the stage on which life unfolds. But it does mean that when we dig to the bottom, we do not find atoms, particles, or even fields in the ordinary sense. We find mathematics. The illusion of matter is the universe's most convincing trick, one that hides the numbers beneath a mask of solidity. So when we ask if reality could be nothing more than a mathematical equation, the illusion of matter provides a startling answer. What you call real is not stuff at all, but equations pretending to be stuff. The solidity of the world is a simulation generated by mathematical laws, and once you see through the illusion, you realize that matter is not the foundation of reality, mathematics is. In the digital age, we are surrounded by information. Every message, every photo, every video we consume is, at bottom, a sequence of bits, ones and zeros. Strangely enough, modern physics suggests that the same might be true of reality itself. Instead of matter or energy being the ultimate foundation, perhaps information is the true bedrock. In this view, the universe is not made of particles or waves, but of data, processed according to mathematical rules. If this is correct, then reality is literally a computation, a living equation unfolding in time. The idea that information might be fundamental began in quantum mechanics. When particles exist in superposition, they are not simply in multiple places at once. They embody different possibilities. Measurement reduces this spread of possibilities to a definite outcome. What collapses is not substance but information, the probabilities encoded in the wave function. Physicist John Archibald Wheeler summarized this idea with the phrase, bit from bit. According to him, everything, every particle, every field, every event, arises from binary choices, yes, no, 1/0, encoded in the fabric of reality. The universe in this sense is digital, at its core. Quantum information theory has reinforced this perspective. Entanglement, one of the strangest features of quantum mechanics, is best understood not as a physical connection, but as an informational one. Two particles can be separated by light years, yet their states remain linked. What connects them is not a hidden signal, but shared information encoded in their joint wave function. The universe does not need wires or channels to maintain this link. It simply operates as an informational whole. Reality, then, looks less like a set of objects and more like a database. Black holes deepen the case. According to classical physics, anything falling into a black hole would be lost forever. But quantum theory suggests otherwise. Information, it turns out, cannot be destroyed. This led to the famous black hole information paradox, where physicists like Stephen Hawking and Leonard Susskind debated whether information falling into a black hole vanishes or is somehow preserved. The current consensus leans toward preservation. Even black holes must encode and release information through radiation. In other words, the universe is not built to lose data. Reality is, at its core, an information-preserving system. This perspective changes how we think about matter and energy. In physics, energy can be converted into matter, and matter into energy. But both can also be represented as information. The arrangement of atoms in a crystal, the sequence of nucleotides in DNA, the firing of neurons in a brain, all are patterns of information. Even the laws of physics themselves can be seen as algorithms, rules for how information evolves. What we call reality may simply be the computation of information by mathematical laws. Consider the analogy of a computer simulation. Inside the game, characters and landscapes seem real, but they are nothing more than data processed by code. Their solidity is an illusion created by numbers, interacting according to rules. In the same way, our universe may be a vast informational system. The particles are not the true reality. The information that defines them is, we do not live in a world of matter, but in a cosmic algorithm, where information is the fundamental unit. This view is supported by surprising crossovers between physics and computer science. The mathematics of error-correcting codes, developed for reliable communication, has found application in quantum mechanics. Some physicists believe the universe itself may operate like an error-correcting code, ensuring stability and consistency in the face of uncertainty. Others explore the possibility that space-time itself emerges from entanglement patterns, meaning that space and time are not fundamental but byproducts of information processing. If so, then even the stage on which reality plays out is informational. What does this mean for us? If reality is information, then consciousness itself may be an informational process. The firing of neurons in the brain, the storage of memory, the flow of thought, all can be seen as patterns of data. Your sense of self, your identity, your memories, all are informational states running on the biological hardware of your brain. In this sense, you are not separate from the informational universe. You are part of it, a unique configuration of data in a vast mathematical system. This perspective also reframes the idea of death and existence. If information is fundamental, then perhaps nothing is ever truly lost. The configuration changes, the data reorganizes, but the information persists in some form. Just as black holes preserve information, so too might the universe as a whole. Reality may be a cosmic memory bank, recording every fluctuation of matter and energy as data in its mathematical ledger. Skeptics might argue that information is just another way of describing matter and energy, not something deeper. But the growing success of information theory in explaining physics suggests otherwise. The equations of information are not decorative. They describe how reality operates at its most basic level. The world is not particles with properties, but information with patterns, and those patterns evolve according to the rules of mathematics. In the end, the informational view of reality aligns perfectly with the idea that existence is a mathematical equation. Information is, by definition, mathematical bits, probabilities, codes, algorithms. If reality is information, then it is already mathematics all the way down. The universe is not built from stuff, but from structure, not from things but from numbers. It from bit may be the simplest way to say it. Everything arises from information, and information is mathematics. From ancient Greece to modern physics, geometry has been humanity's bridge between the visible world and the abstract world of mathematics. The circle, the triangle, the square, these were not just shapes to the Greeks, but keys to understanding reality. Today, as cosmologists map galaxies, trace the curvature of space-time, and explore extra dimensions, geometry remains central. It seems the universe is not only described by geometry, but shaped by it. The cosmos itself may be nothing more than mathematics taking the form of geometry on a vast scale. Einstein's general relativity made this explicit. Gravity is not a force pulling objects, but the geometry of space-time curving under the influence of mass and energy. The planets orbit the sun not because they are tugged invisibly, but because the geometry of space-time directs their paths. A massive object warps the surrounding geometry, and matter follows the curves. When astronomers observe light bending around galaxies in gravitational lensing, they are literally watching geometry shape reality. In Einstein's universe, to understand the cosmos is to understand geometry. But the geometry of the cosmos goes far beyond curves in space-time. At the largest scales, the distribution of galaxies forms a cosmic web, with filaments, clusters, and voids stretching across billions of light-years. This vast structure resembles a mathematical network, a geometry of nodes and connections. Computer simulations of cosmic evolution, using only equations of gravity and dark matter, reproduce this web almost exactly. It is as though the universe itself is solving a geometric equation, arranging matter into structures that follow mathematical patterns of connectivity. Geometry also emerges at the smallest scales. In quantum mechanics, particles are described by wave functions that exist in abstract mathematical spaces. The mathematics of Hilbert space, an infinite-dimensional geometric framework, underpins all quantum behavior. What we call reality is actually playing out in a geometry that exists beyond our ordinary perception, a reminder that geometry is not only visible, but also hidden in higher dimensional mathematics. The mystery deepens when we consider the possibility of extra dimensions. String theory, one of the leading candidates for a theory of everything, proposes that fundamental particles are not points but tiny vibrating strings. The vibrations of these strings give rise to different particles, much like musical notes arising from the vibrations of a violin string. But for the math to work, the universe must have more than the familiar 3 dimensions of space and 1 of time. It requires as many as 10 or 11 dimensions, curled up in intricate geometric shapes known as Calabi-Yau manifolds. These are not decorative details. They determine the very properties of particles and forces. In this view, the geometry of hidden dimensions literally creates the reality we experience. Even in ordinary 3-dimensional space, geometry governs cosmic phenomena. The spiral arms of galaxies, the spherical symmetry of stars, the hexagonal storms on Saturn's poles. These are not random patterns but geometric consequences of physical laws. The geometry of orbits explains eclipses, resonances, and planetary stability. The geometry of waves explains interference, diffraction, and harmony in both sound and light. Everywhere we look, geometry is not just present but essential. Philosophically, geometry's role suggests that space itself is not a stage but a mathematical entity. When we draw a circle or a triangle, we are not inventing those forms but copying structures that exist timelessly. The ratio of a circle's circumference to its diameter, pi, is not a human idea, but a geometric truth of the universe. Whether or not planets exist, pi exists. Whether or not space is curved by stars, the rules of geometry hold. The cosmos, then, may be an instance of eternal geometry written large. What makes this especially compelling is that geometry often reveals truths before observation does. Einstein's prediction of black holes arose directly from the geometry of his equations. Decades before gravitational waves were detected, they were predicted by the mathematics of space-time curvature. Even now, physicists suspect that the geometry of entanglement, the way quantum particles connect, may give rise to space-time itself. If true, then geometry is not a property of the universe. It is the universe. There is also a profound aesthetic to geometry. The universe prefers elegant forms, spirals, spheres, hexagons, lattices. These are not mere accidents of physics, but expressions of deeper mathematical order. Why do soap bubbles form spheres? Because a sphere minimizes surface area, the most efficient geometry. Why do galaxies spiral? Because gravity and rotation produce logarithmic curves. The cosmos favors beauty, because beauty is geometry, and geometry is mathematics. Geometry also links the vast with the intimate. The same equations that describe the curvature of the universe also describe the curvature of your own body in space. The structure of DNA is a double helix, a geometric form. The arrangement of neurons in your brain follows networks reminiscent of the cosmic web. It is as if the universe is repeating geometric patterns at every scale, from galaxies to cells, from space-time itself to your own mind. This universality reinforces the idea that geometry is not decoration but foundation. So what does this mean for the question at hand? If the universe is fundamentally geometric, then it is fundamentally mathematical. Geometry is mathematics given shape, mathematics visible to the senses. The arcs of planets, the spirals of shells, the curvature of space-time, the hidden Calabi or manifolds, all are geometry, and all are mathematics. Reality does not merely obey geometry, it is geometry, and geometry, in turn, is the manifestation of an equation. In the end, the geometry of the cosmos suggests that existence itself is structure, form, ratio, and relation. What we call reality may simply be the visible architecture of mathematics, the universe built not of stuff, but of shapes. The stars, the galaxies, and even the space between them are not things but geometry, echoing the eternal truths of mathematics. The cosmos is a grand design, and its language is geometry. If reality is fundamentally mathematical, then one of the most provocative ideas to emerge in recent years is that we might be living inside a simulation. The simulation hypothesis argues that what we call reality is not the ultimate layer of existence, but a kind of programmed environment, created and run by a higher-level intelligence or system. The very fact that the universe behaves like an equation, consistent, predictable, coded with constants, lends weight to the possibility that it functions like software. And if that is the case, then we may be characters in a cosmic computation. The argument gained traction in philosophy through the work of Nick Bostrom, who framed it as a trilemma. Either civilizations never reach the technological capacity to run vast simulations, or they reach that stage but choose not to simulate conscious beings, or most unsettling, they do run such simulations, and the number of simulated realities vastly outnumbers the original one. If the third option is true, then the odds are that we are living inside a simulation, not outside of it. Statistically, it becomes far more likely that we are code, not creators. What makes the simulation hypothesis compelling is not just philosophy but physics itself. The universe operates with rules that look eerily like programming. The speed of light, for instance, can be seen as a maximum data transfer rate, the fastest the system can process information. Space appears to be quantized at the Planck scale like pixels in a digital image. You cannot zoom in forever because eventually the resolution ends. Quantum mechanics behaves like a probabilistic algorithm, collapsing probabilities into outcomes when observed, as though the system is rendering reality only when needed, much like a video game engine. Furthermore, the stability of physical constants feels like fine-tuning in a program. In computer simulations, certain parameters must be carefully set for the system to run properly. Too much deviation, and the program crashes. Our universe appears to be finely tuned in exactly this way. If gravity, electromagnetism, or nuclear forces were slightly different, reality as we know it would collapse. Why does the universe have such precise constants? One explanation is that they were chosen, as parameters in a simulation, to allow this world to exist. Supporters of the hypothesis point to the idea of computational limits. Energy, information, and entropy all suggest the universe processes information like a computer. The holographic principle in physics, the idea that all information in a volume of space can be encoded on its boundary, resembles data compression in computing. Black holes, rather than being paradoxical pits of destruction, may be cosmic hard drives storing the information of everything they swallow. If the universe behaves like a computer, maybe it is one. Skeptics argue that the simulation hypothesis is unfalsifiable, that it cannot be tested, but others suggest possible clues. If reality is digital, then at its deepest level, space should be grainy, like pixels. Some physicists search for evidence of this discreteness in the cosmic microwave background radiation, or in the highest energy cosmic rays. If a fundamental lattice of space-time exists, it would be like discovering the pixels in the screen of our universe. That would suggest we are not in a smooth continuum, but in a programmed grid. The hypothesis also raises profound questions about consciousness. If we are simulated, does that make us less real? Perhaps not. If consciousness arises from information processing, then a simulated brain running in a sufficiently detailed system could experience reality just as vividly as an organic brain. In that case, the distinction between real and simulated collapses. Reality for us is whatever we experience, whether generated by atoms or algorithms. If the universe is a simulation, then this life, these experiences, and these thoughts are as real to us as they would be in any other form. There is also an unsettling theological parallel. The simulation hypothesis echoes ancient ideas of creation, a higher power designing the universe, setting rules, and watching its inhabitants unfold. In this modern version, the gods are programmers, the laws are algorithms, and the creation is a running simulation. Whether that programmer is another species, a future version of humanity, or something beyond imagination, the resemblance to myth is striking. Perhaps what religions intuited as divine order is in fact mathematical order expressed in code. But even if the simulation hypothesis is true, it does not necessarily diminish meaning. If we are in a simulation, then so is everything we love and experience. Our choices, our relationships, our creativity, all remain real within the framework we inhabit. In fact, knowing that reality is mathematical code might enrich meaning. It would mean we are not adrift in chaos, but participants in a structured, comprehensible system. Reality becomes not less real but more profoundly mathematical. Ultimately, whether or not we are simulated, the hypothesis underscores the same core truth. The universe behaves like mathematics. The constants, the quantization, the rules, the patterns, all point to a reality that looks less like matter and more like code. Whether the coder is nature itself or a higher intelligence, the conclusion is similar. Reality is a computation, an equation unfolding moment by moment. So when we ask if reality could be nothing more than a mathematical equation, the simulation hypothesis gives us one of the boldest answers: yes, and perhaps the equation is running on a cosmic computer. The stars, the galaxies, your very thoughts, all may be lines of code written in a language older than humanity. And whether this is design, accident, or inevitability, the result is the same. Reality is mathematics, simulated or not. If mathematics underlies the universe, then surely it must also run through the most mysterious phenomenon of all, consciousness. The fact that we experience the world, that we are aware of ourselves and our surroundings, seems at first to resist the cold precision of equations. Consciousness feels fluid, subjective, full of color and texture. Yet when researchers peer beneath the surface, they often find patterns, numerical, structural, and mathematical, that govern even our inner experience. At its foundation, the brain is a vast network of neurons firing electrical signals. Each neuron either activates or stays quiet, producing binary-like states not unlike the zeros and ones of digital code. When billions of these tiny units interact, they create the symphony of thought, memory, and perception. Mathematical models of neural networks show how patterns of activation ripple across the brain, forming the basis for attention, decision-making, and even emotion. What feels like a flowing stream of awareness may actually be the outcome of underlying computational rhythms. One striking discovery is the importance of oscillations, rhythmic cycles of activity in the brain. Neuroscientists measure brain waves, such as alpha, beta, and gamma rhythms, which correspond to different states of consciousness. Sleep, for example, shows slow delta waves, while deep focus involves faster gamma waves. These oscillations follow mathematical frequencies, like repeating sine waves, and they synchronize across brain regions, coordinating perception and thought. Consciousness, then, can be described as a dance of oscillatory patterns, a kind of mathematics in motion. Information theory adds another layer. Consciousness may be the process of integrating information across different parts of the brain. Giulio Tononi's integrated information theory proposes that consciousness corresponds to the quantity of information integration, a value that can in principle be measured mathematically. According to this idea, the richer the integration, the more vivid the conscious experience. A human brain, with its dense network of connections, integrates far more information than, say, a thermostat, and thus produces a far deeper level of awareness. The measure, known as phi, is explicitly mathematical, suggesting that consciousness is not outside the domain of numbers, but expressible through them. Patterns also emerge in how consciousness perceives reality. Optical illusions, for instance, reveal that the brain applies probabilistic calculations to interpret the world. When faced with ambiguous input, the brain predicts what it is most likely to see, creating illusions when its assumptions don't match reality. This Bayesian approach, constantly updating beliefs based on probabilities, is mathematical at its core. Our very perception, then, is shaped by equations running behind the scenes. Language and thought, too, rely on patterns. Sentences follow rules of syntax, logic follows structures of inference, and even emotions often align with predictable feedback loops between brain chemistry and behavior. Music, one of the most powerful emotional experiences, is deeply mathematical, built on rhythm, harmony, and proportion. That music can move us so profoundly suggests that consciousness resonates with mathematical patterns, as if our inner worlds are tuned to equations. Some researchers take this further, suggesting that consciousness itself may be a fundamental property of the universe, like space, time, and mass. If so, then mathematics may not just describe consciousness, but constitute it. Consciousness could be seen as the unfolding of certain mathematical structures, such as networks of information flow. In this view, our subjective experience is not an anomaly in a material world, but a manifestation of the universe's informational mathematical nature. This has profound implications for artificial intelligence. If consciousness arises from information integration and patterns, then a sufficiently advanced AI built on complex mathematical architectures might one day experience awareness. Already, neural networks mimic aspects of human cognition, generating language, recognizing images, and solving problems. Whether they are truly conscious or simply simulating thought remains debated, but the very question underscores how tightly consciousness and mathematics are intertwined. There is also a mystical dimension. Many spiritual traditions describe consciousness as patterned vibrations or energy flows. Modern neuroscience translates those metaphors into measurable brain activity. Meditation, for instance, alters oscillatory rhythms, shifting the balance between brainwave states. The calm clarity described by practitioners correlates with changes in mathematical patterns of neural synchronization. What ancient mystics intuited as harmony, science now measures as coherence in oscillatory frequencies. Yet the question remains, can mathematics fully capture the essence of consciousness? Equations can describe the mechanisms, the firing of neurons, the integration of information, the flow of oscillations, but can they capture the subjective feeling of being alive? The so-called hard problem of consciousness asks why any of this feels like something from the inside. Why does a brain, processing information mathematically, generate the taste of coffee, the color red, or the ache of loss? Mathematics may describe the structure, but whether it explains the raw texture of experience remains uncertain. Still, even if mathematics cannot explain everything, it clearly pervades consciousness. The patterns of neural activity, the frequencies of oscillations, the algorithms of perception, the logic of thought, all reflect mathematical structure. Consciousness, far from being outside of mathematics, seems to emerge from it. The self you experience, the thoughts moving through your mind right now, are not random but structured by patterns describable in equations. If reality is a mathematical equation, then consciousness is not an exception. It is one of the most complex solutions to that equation, a living pattern of information processing that reflects the universe's mathematical order. When you close your eyes and imagine, when you feel joy or despair, when you reflect on reality itself, all of it is built on patterns, rhythms, and structures as precise as any equation. Consciousness, like the cosmos, may be mathematics brought to life. When we think of mathematics, our minds usually drift toward physics, cosmology, or the abstract purity of equations. But the deeper scientists look into the living world, the more they discover that life itself is saturated with numbers, ratios, and mathematical patterns. From the spiral of a sunflower to the heartbeat in your chest, biology whispers in the language of mathematics. If reality is a mathematical equation, biology is its most poetic solution. One of the most famous examples is the Fibonacci sequence, a simple progression of numbers where each new term is the sum of the two before it. 1, 1, 2, 3, 5, 8, 13, and so on. Astonishingly, this sequence appears throughout nature. The spiral arrangement of seeds in a sunflower, the scales of a pine cone, the branching of trees, and even the shells of nautilus sea creatures often follow Fibonacci spirals. Why? Because this sequence allows optimal packing and growth, minimizing wasted space and maximizing efficiency. Nature, without consciously calculating, selects mathematical solutions for survival. The golden ratio, closely tied to Fibonacci numbers, also appears in living organisms. This irrational number, approximately 1.618, has been called the divine proportion. In human faces, seashell spirals, and even DNA molecules, the golden ratio shows up again and again. Artists and architects have long used it for aesthetic harmony, but in biology, it seems to appear as a practical result of efficient growth patterns. That beauty itself may be a reflection of mathematical efficiency, suggests that our sense of aesthetics is wired into nature's equations. Beyond spirals and ratios, mathematics appears in the rhythm of life. Your heartbeat, for example, is not a simple metronome, but a complex mathematical system. The variation in intervals between beats, known as heart rate variability, follows fractal patterns. These patterns indicate health and adaptability. Too regular, and the heart is fragile. Too chaotic, and the system collapses. Life thrives at the edge between order and chaos, in a mathematically describable zone where adaptability and stability balance. The same principle applies to breathing rhythms, neural firing, and hormonal cycles. These oscillations can be described by mathematical functions, showing how biology relies on precise timing and patterned variation. Even your sleep cycle, with its stages of REM and non-REM sleep, follows repeating rhythms measured in predictable intervals. The mathematics of oscillations is not only written into the cosmos, but also beats inside our bodies. Genetics brings another layer of numerical beauty. DNA, the blueprint of life, can be understood as a code composed of 4 nucleotides: adenine, thymine, cytosine, and guanine. Sequences of these nucleotides form the instructions for building proteins, and these sequences can be analyzed like strings of code. The genetic code is a symbolic language, reducible to combinations and permutations, a field of mathematics. Lob mutations, recombination, and inheritance follow probabilistic rules that biostatistics and population genetics use to predict evolutionary outcomes. Evolution itself, often thought of as a random process, can be modeled through equations describing selection pressures, mutation rates, and fitness landscapes. Even at larger scales, biology follows mathematical patterns. The branching of rivers resembles the branching of blood vessels, trees, and lungs. This similarity is no coincidence. It reflects fractal geometry. Fractals allow efficient distribution systems, ensuring that nutrients, oxygen, or water reach every corner of a structure. Your lungs, with their billions of tiny alveoli, are fractal in design, maximizing surface area for gas exchange within a limited volume. This efficiency is pure mathematics embedded in your body. The growth of populations also follows predictable equations. The logistic growth curve, for example, describes how a population expands rapidly before leveling off as resources become limited. Predator-prey dynamics, captured by the Lotka-Volterra equations, model how rabbits and foxes, or any two species in competition, rise and fall in response to each other. These equations reveal the deep interplay of mathematics and ecology, showing how even the chaotic struggle for survival follows hidden numerical order. Biology even reveals mathematics in its symmetries. Many animals and plants exhibit bilateral symmetry, 2 mirrored halves, or radial symmetry, like a starfish or daisy. These symmetries are not just aesthetic but functional, shaped by mathematical principles of stability and efficiency. Developmental biology studies how such symmetries emerge from genetic instructions, often through equations describing gradients of chemical signals that guide cells into position during embryonic growth. Even disease and healing can be analyzed mathematically. The spread of epidemics follows models like the SIR susceptible, infected, recovered equations, which predict infection peaks and thresholds for herd immunity. Cancer growth, too, can be modeled as an uncontrolled replication process, following exponential functions until constrained by treatment or immune response. Mathematics provides tools for understanding and potentially controlling these processes, highlighting how numbers shape even the most personal aspects of health. At the microscopic level, proteins fold into complex three-dimensional shapes, essential for their function. The folding problem, long a mystery, is governed by rules of energy minimization. Another mathematical principle, artificial intelligence systems like AlphaFold, now predict these structures with stunning accuracy by applying mathematical modeling and probability. What once seemed inscrutable randomness reveals itself as mathematically patterned necessity. The more we uncover, the clearer it becomes. Life is not opposed to mathematics, but an expression of it. Every heartbeat, every leaf pattern, every neuron firing in your brain is part of an intricate numerical order. To say that reality might be nothing more than a mathematical equation is not to diminish life, but to highlight its hidden elegance. The vibrancy of biology, from the curve of a seashell to the flutter of a hummingbird's wings, is the universe solving equations in living form. And there is an even deeper implication. If life follows mathematics, then the distinction between biology and physics begins to blur. The same fractals that shape galaxies shape lungs. The same probability that guides quantum particles guides genetic mutations. The same oscillations that govern planetary orbits govern brainwaves. Life in this sense is the universe's mathematics folded into patterns that can breathe, grow, and dream. So when you look at a flower spiraling open, when you hear your heartbeat, when you watch a flock of birds turn as one, you are witnessing mathematics alive and in motion. Biology is not an exception to the mathematical universe. It is its most eloquent expression. At first glance, a coastline, a fern leaf, or a lightning bolt may look chaotic, irregular, even impossible to capture with neat geometry. Yet when mathematicians began studying these shapes, they uncovered a startling truth. Nature's chaos is patterned, and those patterns repeat endlessly at different scales. This is the world of fractals, shapes that reveal infinite complexity hidden within finite boundaries. To speak of reality as a mathematical equation is to acknowledge that infinity is not an abstract concept floating in a textbook. It is written into the very fabric of existence. The term fractal was coined by mathematician Benoit Mandelbrot in the 1970s. Though the patterns themselves had been observed long before, a fractal is a shape that exhibits self-similarity, meaning parts of it resemble the whole. Zoom in on a fern's leaf, and you find that each tiny leaflet resembles the larger frond. Zoom into a Romanesco broccoli, and its spiraling cones are made of smaller spirals, repeating the same geometry. Infinity is contained in miniature, nested inside every scale. One of the most iconic fractals is the Mandelbrot set, a mathematical object generated by a deceptively simple equation. Ses equals sine ses when plotted on a complex plane. This recursive formula produces an endlessly intricate boundary. No matter how deep you zoom into its edges, new forms emerge, spirals, tendrils, miniature replicas of the whole. The set demonstrates that infinite detail can arise from simple mathematical rules, an echo of how the universe itself might emerge from fundamental equations. Fractals appear not only in mathematics but everywhere in nature. Coastlines are a perfect example. Early attempts to measure their length yielded absurd results because the length depends on the scale of measurement. A ruler of 100 kilometers might smooth over inlets and bays, while a ruler of 1 meter reveals countless tiny curves and jagged edges. The closer you look, the longer the coastline becomes, approaching infinity. This paradox reflects fractal geometry: finite area, infinite boundary. The branching patterns of rivers, trees, and blood vessels also reveal fractal structure. A river splits into tributaries, which split again into smaller streams, mirroring the branching of veins in a leaf or capillaries in your body. These fractal structures maximize efficiency. Rivers drain landscapes, lungs distribute oxygen, and trees gather sunlight, all by repeating simple branching patterns at multiple scales. The universe seems to favor fractals because they balance growth, efficiency, and adaptability, nature's optimization through mathematics. Fractals also emerge in chaotic systems. Lightning forks in fractal paths, turbulence in fluids creates fractal vortices, and clouds billow in fractal layers. Even the fluctuations of the stock market display fractal-like irregularities. These patterns suggest that chaos, far from being random, is structured by hidden mathematics. Infinity is not only theoretical but operational, shaping the behavior of systems too complex for linear equations. Perhaps most fascinating is the role of fractals in the human body. Your lungs, as mentioned earlier, are fractal in design, but so too is your circulatory system. Each artery branches into smaller vessels, down to microscopic capillaries. This repetition ensures every cell receives nutrients and oxygen. Even the neurons in your brain extend dendrites in fractal patterns, maximizing connections across networks. Your body is a living fractal, a biological equation solving for survival. Fractals also connect deeply with perception and aesthetics. Studies show that humans are naturally drawn to fractal patterns. We find them pleasing, calming, even mesmerizing. This may be because our visual and cognitive systems evolved within a fractal world: forests, mountains, rivers, and clouds. When we look at fractal art or natural scenery, our brains recognize familiar mathematics. The beauty we feel may simply be recognition of the infinite patterns we ourselves are built upon. Infinity, however, is not without its paradoxes. A fractal can have a finite area, but an infinite perimeter. It can be infinitely detailed, yet bounded in space. The Koch snowflake, for instance, begins with a simple triangle. By adding smaller triangles to each side, and then repeating the process infinitely, you create a shape with infinite perimeter, yet finite area. Such paradoxical objects challenge our intuition, but they follow strict mathematical rules. If reality is fractal, it may be simultaneously finite and infinite, limited yet unbounded. Fractals also invite us to reconsider time and scale. If patterns repeat infinitely, then the universe might not have a smallest or largest scale. Galaxies cluster in fractal webs, stars form in fractal clouds of gas, and subatomic particles dance in chaotic fields. The same structures appear across vastly different scales, suggesting reality itself could be self-similar, a grand fractal equation unfolding endlessly. In science, fractals have practical power. They are used in computer graphics to simulate natural landscapes, in medicine to model heart rhythms and tumor growth, and in technology to design antennas that capture multiple frequencies. Even music and language reveal fractal patterns, where rhythms and structures repeat at different scales. The reach of fractals across disciplines reinforces the idea that they are not incidental but fundamental to reality. What do fractals say about existence? They whisper that infinity is not outside us but within us. That complexity emerges not from chaos, but from repetition of simple rules. That beauty, efficiency, and survival all spring from recursive mathematics. The fern leaf, the thunderstorm, the neural network, all are chapters in the same fractal book. If reality is a mathematical equation, then fractals are its recursive loops, endlessly writing and rewriting themselves at every level of existence. To see a fractal is to glimpse infinity made tangible. The jagged edge of a coastline, the branching of a tree, the spiral of a galaxy, all are reminders that the infinite hides in plain sight, woven into the finite. Infinity, once thought unreachable, is etched into every leaf and every breath. The idea that mathematics can describe the present is already astonishing, but even more extraordinary is its power to predict the future. From the orbits of planets to the spread of diseases, from financial markets to weather systems, equations do not merely record reality, they project it forward, revealing what has not yet happened. If reality is nothing more than a mathematical equation, then perhaps the future is already written within its logic, waiting only to unfold. This predictive power began most famously with Isaac Newton's laws of motion. By combining simple equations with universal gravitation, Newton demonstrated that the trajectory of a cannonball or the orbit of a planet could be calculated in advance. Suddenly the heavens were no longer mysteries but solvable problems. Astronomers used Newton's equations to predict the return of Halley's comet decades before it appeared. Such successes suggested that the universe operated like a deterministic machine, its future encoded in mathematical form. Later, Pierre-Simon Laplace took this idea further, with his thought experiment of a superintelligence, often called Laplace's demon. If such an intellect knew the exact position and momentum of every particle at one moment, it could calculate the past and predict the future with absolute certainty. The universe, in this vision, was like a colossal equation. Input the present, and the future emerges inevitably. Although modern physics complicates this picture, the ambition to forecast reality remains at the heart of science. The predictive reach of mathematics extends far beyond celestial mechanics. Consider epidemiology, equations modeling infection rates, recovery times, and transmission probabilities allow scientists to forecast the spread of diseases. These models guided public health decisions during pandemics, estimating peaks of infection and the impact of interventions. While not flawless, the predictions often align closely with real outcomes, showing that even the chaos of human behavior bends to mathematical probabilities. Weather prediction is another triumph of mathematics. The atmosphere is a turbulent, chaotic system, yet equations rooted in fluid dynamics allow meteorologists to project storms, rainfall, and temperature changes days in advance. Satellites provide real-time data, which equations transform into forecasts. Though long-term predictions remain uncertain, the ability to foresee hurricanes or droughts illustrates mathematics as a window into the future. In this sense, weather maps are snapshots of equations unfolding through time. The same applies in economics and finance. Models built on probability, statistics, and game theory attempt to predict market movements. While human psychology introduces uncertainty, patterns emerge from the equations governing trade, debt, and growth. Financial crises often reveal the limits of prediction, yet even these collapses can sometimes be anticipated by stress-testing mathematical models. Reality's economic side, too, reveals itself through numbers that lean forward into time. In physics, prediction reaches cosmic extremes. Albert Einstein's general relativity not only explained the bending of light and the motion of planets, but also predicted black holes, gravitational waves, and the expansion of the universe, phenomena confirmed decades or even a century later. Similarly, the standard model of particle physics predicted particles like the Higgs boson long before they were observed experimentally. These triumphs underscore a profound truth. Equations often know more about reality than we do. Yet prediction is not absolute. Quantum mechanics introduced uncertainty into physics, suggesting that outcomes cannot be forecast with certainty, but only with probabilities. Heisenberg's uncertainty principle ensures that Laplace's demon will never exist. Still, even here, mathematics provides predictive power. Quantum equations forecast probabilities of outcomes with staggering accuracy, enabling technologies from semiconductors to MRI machines. The future may not be deterministic, but it remains mathematically describable. Prediction also arises in the domain of artificial intelligence and data science. Algorithms trained on vast datasets use mathematical structures to anticipate human behavior, from what you might buy online to the routes of traffic in a city. These predictions often feel uncanny, as if reality's next steps were already written in statistical code. The success of machine learning suggests that human choices, too, may follow hidden equations, no less predictable than the orbit of a planet. The philosophical implications are enormous. If mathematics can predict so much of reality, does that mean the future is already contained within the equations? Are we simply actors in a script, pre-written by numbers? Or are the equations themselves only approximations, hints of deeper structures we have not yet uncovered? The tension between determinism and uncertainty lies at the heart of this question, and mathematics plays both roles, offering certainty in some domains, probability in others. The ability of mathematics to predict also raises the possibility that time itself is an illusion. If the future is already encoded in the equations, then past, present, and future may coexist in a timeless structure. From this perspective, we do not move through time, we traverse an equation, step by step. Prediction then is not foresight, but recognition of what is already inscribed in the fabric of reality. Mathematics also predicts beyond Earth. Models of stellar evolution forecast how stars are born, live, and die. Equations predict the ultimate fate of galaxies, and even the universe itself. Will the cosmos expand forever into a cold void, collapse back into a singularity, or oscillate endlessly between extremes? The answers, cosmologists believe, lie not in speculation but in equations already written, waiting for the right measurements to reveal which future is true. Of course, prediction has limits. Chaos theory reminds us that tiny differences in initial conditions can lead to vast divergences in outcomes. The proverbial butterfly's wings can alter the path of a hurricane. This sensitivity does not mean mathematics fails, rather it highlights that equations sometimes describe possibilities, not certainties. The future is not always a single thread, but a branching tapestry of mathematical potentialities. Still, the fact remains, equations consistently illuminate tomorrow. Whether in predicting eclipses, modeling epidemics, or anticipating technological innovation, mathematics proves itself again and again as a lantern shining into the unknown. Reality, far from being unpredictable chaos, bends to the logical unfolding of numbers. If reality is a mathematical equation, then prediction is simply the act of reading further down the line. The future is already present in the structure, waiting to be calculated, discovered, or revealed. Each forecast, whether of a comet or a quantum state, whispers the same truth: the numbers know what comes next. Perhaps they know more than we dare to admit. Imagine reality not as a flowing, continuous fabric, but as something pixelated, chopped into the tiniest possible units, like a cosmic video game running on an invisible computer. This is the essence of digital physics, the idea that the universe itself is discrete, computational, and fundamentally mathematical in structure. Just as images on a screen are built from pixels, perhaps all of reality is constructed from indivisible bits of information, processed by equations deeper than matter or energy. The seeds of digital physics were planted with the rise of computers in the 20th century. Physicists began to wonder, if our machines could simulate complex realities with lines of code, might the universe itself be operating on a similar principle? John Archibald Wheeler, a renowned physicist, condensed the idea into 3 famous words: it from bit. By this he meant that every particle, every field, every law of physics ultimately emerges from binary choices: yes, no, 1, 0th. Information as the bedrock of existence. Digital physics suggests that space and time themselves may not be continuous, but quantized. Instead of an infinitely smooth fabric, the universe would be like a digital grid, with finite resolution. Just as you cannot zoom into a pixel beyond its boundary, you cannot infinitely divide space and time. The Planck length, about 10 circumflex 35 meters, and the Planck time, about 10 circumflex 44 seconds, may represent this cosmic pixel size. Beyond these scales, reality may not exist in the form we imagine, because everything beneath is simply code. This viewpoint also offers potential explanations for puzzling aspects of modern physics. Quantum mechanics, with its probabilistic nature, could be interpreted as the processing rules of the cosmic computer. The apparent randomness in quantum events may not be true chaos, but rather the output of deterministic algorithms running beyond our perception. Just as a video game character experiences only the rendered world but not the underlying code, we too may only see the equation's surface. One striking piece of evidence comes from how mathematics behaves in physics. Digital simulations of fluid flow, particle interactions, or even galaxies often recreate phenomena remarkably close to the real universe. If equations inside our computers can mimic reality so convincingly, is it a stretch to imagine that reality itself is running on an infinitely more advanced processor? In this sense, our attempts to simulate the cosmos are not artificial. They may be reflections of how the cosmos already computes itself. Another implication of digital physics is that information may be more fundamental than matter. A rock, a star, or a brain would not be the ultimate building blocks of reality, but instead, arrangements of information bits structured according to equations. Energy and particles are byproducts of information processing. This aligns with discoveries in quantum information theory, where scientists describe particles less as things and more as information states evolving under mathematical rules. The theory even intersects with black holes. According to Stephen Hawking and others, black holes contain finite amounts of information, proportional not to their volume but to their surface area, a bizarre insight known as the holographic principle. This hints that the universe itself may be holographic, storing its information like a compressed digital file on a cosmic boundary. The physical world we perceive could be the decoded output of this information storage system. Philosophically, digital physics resonates with the simulation hypothesis, the proposal that our universe might be a simulated environment created by advanced intelligences. If reality is fundamentally digital, then simulating it is not only possible, but perhaps inevitable. Every particle interaction is already a kind of computation, and our own computers, primitive by cosmic standards, are beginning to mimic such processes. From this angle, the line between natural and simulated dissolves. Reality is computation, either way. Critics argue that digital physics risks oversimplifying the richness of the universe. Continuous mathematics has served physics extraordinarily well, from calculus describing planetary motion to differential equations modeling electromagnetic fields. Why should we assume reality is digital, when continuity has explained so much? Yet proponents counter that beneath the smoothness lies discreteness. Just as digital photographs appear continuous until magnified, reality may be continuous in experience, but digital at its root. The theory also faces technical challenges. No one has yet built a fully successful digital model of the universe, though tantalizing hints exist. Some physicists explore cellular automata, simple rule-based systems like Conway's game of life, as analogies for how complex realities might emerge from simple binary processes. Others study lattice-based models of space-time, where equations replace the continuous background of relativity with discrete grids. While incomplete, these efforts reveal the plausibility of digital foundations. What makes digital physics so compelling is its blend of science and philosophy. It suggests a universe where the most fundamental reality is not particles or waves but computation, equations unfolding like code. Consciousness, matter, energy, even the flow of time would then be emergent phenomena, illusions created by mathematical processing. The universe would be less like a cosmic poem and more like a cosmic program, running inexorably forward. Still, the poetic beauty remains. For if reality is digital, then everything we know is built from patterns of ones and zeros, woven into the grandest tapestry imaginable. Every sunrise, every thought, every galaxy would be a line of code in the ultimate equation. Perhaps we are not spectators, but participants, both reading and writing the script as it unfolds. In this vision, to ask whether reality is real or simulated may miss the point. The deeper truth is that reality is computational, and mathematics is its language. The equations are the universe. The universe is the equations, and we are the living expressions of that digital song. If reality truly is mathematical, if every star and cell and thought emerges from equations, then an unsettling question follows: are equations enough? Can mathematics capture the full essence of existence, or are there limits to what it can describe? This tension sits at the heart of both philosophy and physics. For every dazzling success of mathematics in explaining the universe, there are also boundaries where the numbers falter and mysteries remain unsolved. Consider first the triumphs. Newton's equations of motion predicted planetary orbits with stunning accuracy. Maxwell's equations unified electricity and magnetism. Einstein's field equations bent space and time into a coherent picture of gravity. The standard model of particle physics is essentially a vast equation sheet describing nearly every fundamental particle interaction ever observed. In many ways, equations are the scaffolding of reality, holding everything upright, but cracks appear the deeper we look. Take chaos theory, for instance. Even with exact equations in hand, some systems defy precise prediction. Weather is the classic example, governed by well-known mathematical laws, yet utterly unpredictable beyond a few days due to sensitive dependence on initial conditions. The equations don't fail, but their usefulness in practice does. This reveals a paradox. Knowing the math doesn't always give us mastery over the world. Sometimes the very complexity of the equations creates an unbridgeable gap between theory and prediction. Another boundary is Gödel's incompleteness theorems, which state that in any sufficiently powerful mathematical system, there are truths that cannot be proven within that system. If mathematics is the foundation of reality, this suggests that even within the code of the cosmos, there will always be truths that escape proof. The universe may contain unprovable facts, unreachable by equations, forever lingering just beyond the grasp of logic. Quantum mechanics provides another example of mathematical limits. Its equations are among the most accurate in science, predicting particle behaviors to incredible precision, yet they operate probabilistically, not deterministically. When we calculate the probability of an electron's location, we are not describing certainty, but likelihood. Does this mean the equations are incomplete, or that randomness is baked into the universe itself? Either way, mathematics seems to confront a horizon of unknowability. Equations also struggle with the problem of consciousness. Physics can describe neurons firing, electrical patterns in the brain, and the chemical dynamics of neurotransmitters. But can equations alone explain the subjective experience of being, the redness of red, the sound of music, the feeling of love? These qualia may resist reduction to mathematics. Some philosophers argue that consciousness exposes the ultimate limit of equations. They may explain how the brain functions, but not why experience exists. Another boundary appears in the clash between general relativity and quantum mechanics. Both rely on equations, and both describe the universe with remarkable success. Yet when combined, for instance, inside black holes, or at the birth of the universe, their equations break down. They become nonsensical infinities, a mathematical dead end. This signals that our current equations are incomplete, mere approximations of a deeper, unified framework we have yet to discover. Even when equations work, They raise questions of interpretation. Are they discovered or invented? Do they reveal the universe as it truly is, or do they simply describe patterns we observe? The same mathematical laws can often be written in multiple ways, each equally valid. Is one the real equation of the universe, or are they all human approximations of something ineffable? If mathematics is only a lens, then perhaps it distorts as much as it reveals. The human element itself introduces limits. Equations are written, solved, and interpreted by us, creatures with finite brains and bounded perception. The universe may be an infinite equation, but can finite minds ever fully grasp it? Just as an ant cannot comprehend the architecture of a cathedral, we may be forever constrained by the narrowness of our cognition, no matter how advanced our mathematics becomes. Still, these limits do not diminish the wonder of equations. They deepen it. Each failure or horizon becomes an invitation to expand. Chaos led us to new mathematics of complexity. Gödel's incompleteness inspired fresh philosophical inquiry. Quantum indeterminacy spurred the creation of quantum information theory. Even the stubborn mysteries of consciousness have motivated new fields at the intersection of physics, neuroscience, and philosophy. Every crack in the mathematical wall reveals a doorway to a larger vision. Ultimately, the limits of equations remind us that mathematics, for all its beauty, may not be the whole story. It might be the skeleton of reality, but not its flesh, the script, but not the performance, the code, but not the lived experience of the program. The heartbeat of the universe might pulse partly beyond numbers, in domains we cannot yet quantify. And yet, paradoxically, even the recognition of these limits often comes through mathematics itself. We discover chaos, incompleteness, and quantum indeterminacy through equations that show us where they break. It is as though mathematics itself is whispering, "I am not infinite. I can take you far, but not all the way." This doesn't mean reality escapes mathematics entirely. It may still be fundamentally mathematical, but with layers that exceed our ability to compute, prove, or imagine. Equations may form the cosmic bedrock, but their expression in reality, consciousness, life, beauty, mystery, spills over the mathematical container. Perhaps the final lesson is humility. Equations are astonishing tools, but they may never give us total mastery. The universe is not a puzzle to be solved once and for all. It is a living mystery, partly expressed in numbers, partly in silence. To embrace the limits of equations is not to surrender, but to recognize that the infinite cannot be fully captured, not even by mathematics itself. Behind every mathematical triumph lies a deeper question. What is mathematics, really? Is it something we invent, or something we discover? This philosophical puzzle has haunted thinkers for centuries, and it strikes at the very core of the idea that reality might itself be a mathematical equation. If mathematics is only a human invention, then how can it be the foundation of reality? But if mathematics is discovered, an eternal truth that exists outside of us, then perhaps the universe really is written in its language. Philosophers have split into two broad camps on this question. On one side stand the Platonists, who argue that mathematical objects exist independently of human minds. Numbers, equations, and geometrical forms are not creations, but discoveries, eternal truths waiting for us to stumble upon them. Just as the planet Neptune existed long before telescopes revealed it, so too did the number pi exist long before humans calculated its digits. For Platonists, when Einstein discovered relativity, or when Pythagoras identified the right triangle theorem, they weren't inventing, they were uncovering eternal truths. On the other side, stand the nominalists or constructivists, who see mathematics as a human-made language, a set of symbols and rules we devised to model the world. According to this view, numbers don't exist in the same way chairs and trees do. They are abstractions, mental tools invented to track sheep, measure land, and build civilizations. Equations are ingenious human constructs, but without us, they vanish. A universe without minds would still exist, but it would not contain numbers unless beings like us invented them. This debate carries profound implications. If mathematics is discovered, then reality itself must be mathematical in essence. Our equations work because they mirror the deep architecture of the universe. But if mathematics is invented, then its uncanny success in describing nature becomes a puzzle. Why should a human-made system of symbols line up so perfectly with galaxies, particles, and DNA? This is the so-called unreasonable effectiveness of mathematics, famously described by physicist Eugene Wigner. Consider geometry. Ancient Egyptians used practical geometry to measure farmland after the Nile's floods. The Greeks later formalized it into a deductive system of proofs. Was geometry lying in wait in the structure of space itself, or was it only codified by clever minds observing patterns? Similarly, algebra and calculus arose from human attempts to solve real-world problems, yet their reach extended far beyond their original purposes. Newton developed calculus to explain motion. Today it underpins everything from quantum physics to computer algorithms. Did humans invent a trick that just happened to align with the cosmos, or did they tap into an eternal structure? There are also intermediate positions. Some philosophers suggest that mathematics is both invented and discovered, invented as a language, discovered in its consequences. When we invent the rules of chess, we also discover that checkmate is possible, or that certain strategies emerge. Similarly, when we invent the axioms of arithmetic, we simultaneously discover truths that flow logically from them, whether or not they have any direct application. Another angle is the embodied mind hypothesis, which argues that mathematics arises from the structure of human cognition. Our brains evolved to perceive space, time, and quantity, and mathematics is an abstraction of those perceptions. We are good at counting because counting helped our ancestors survive. From this view, mathematics reflects both the universe and the peculiar shape of our own minds. In this sense, math is a dialogue between cosmos and consciousness. Philosophy of mathematics also asks about the limits of what math can capture. Can mathematics explain art, love, or morality? Some argue yes, that even these are reducible to information, patterns, and equations. Others resist this reduction, claiming that the richness of human life cannot be fully quantified. This debate echoes the earlier discussion of consciousness. Mathematics explains much, but does it explain everything? Interestingly, even physicists often disagree on these philosophical questions. Roger Penrose, for instance, leans toward Platonism, believing that mathematical structures have a real existence outside human thought. Stephen Wolfram, on the other hand, suggests that mathematics is simply one possible formal system among many, and we use it because it works for us. Max Tegmark goes even further, proposing the mathematical universe hypothesis, which claims the universe is not merely described by mathematics, but is mathematics. If mathematics is invented, then reality is something deeper, and equations are only shadows of it. If mathematics is discovered, then equations may be the very bones of reality itself. Either way, the mystery intensifies. Why do equations not only describe reality, but often predict it with uncanny accuracy? Why does mathematics allow us to foresee phenomena we've never observed, like black holes or antimatter, which were later confirmed by experiments? Perhaps the philosophy of mathematics teaches us humility. We may never fully resolve whether math is discovered or invented, but in either case, its role in shaping our understanding of reality is undeniable. We live in a world where numbers unlock mysteries, from the spiral of galaxies to the code of DNA, from the expansion of the universe to the rhythm of our own hearts. Whether we created mathematics or uncovered it, it has become the closest thing we have to a universal truth. In the end, the philosophy of mathematics points us back to the central mystery of existence. Numbers and equations may be tools, or they may be the essence of reality. They may be inventions of the mind, or discoveries of the cosmos. But either way, they have become bridges between thought and being, between mind and universe. And perhaps it is on these bridges, fragile, eternal, imperfect, and astonishing, that we truly encounter the mathematical heart of reality. When we talk about mathematics, it's easy to imagine it as a purely human affair. Chalk dust on a blackboard, scribbled equations in notebooks, elegant proofs debated by philosophers and scientists. But what if mathematics extends far beyond our species? What if it is a universal language, written into the fabric of existence itself, one that any intelligence, human, alien, or artificial, would inevitably encounter? The question matters, because it reveals whether mathematics is truly the essence of reality, or simply a clever human invention. If mathematics is only a cultural artifact, then alien civilizations might operate with completely different systems of thought, perhaps unrecognizable to us. But if mathematics is universal, then no matter how strange or alien a mind might be, it would eventually uncover the same truths: prime numbers, geometric ratios, physical constants. One way scientists have tested this idea is by looking at the most basic structures of mathematics. Take prime numbers, for example. They are the building blocks of arithmetic, indivisible and fundamental, whether you count sheep, stars, or electrons. Eventually the concept of prime emerges. It doesn't matter what symbols you use or how you represent them. Primes are unavoidable. This is why prime numbers were chosen in the Arecibo message, a radio signal sent into space in 1974. Encoded in the message was a pattern based on prime numbers, under the assumption that any intelligent life would recognize their significance. Similarly, geometry seems to transcend culture and biology. The ratio of a circle's circumference to its diameter, pi, is not a human creation. It is embedded in the very definition of what a circle is. No matter what planet you live on, or what senses you evolved, if you measure circles, you will encounter pi. Likewise, the Pythagorean theorem will hold in every possible world where right triangles exist. This is why many scientists argue that mathematics is not ours, but universal. Yet there's another side to the story. Some anthropologists point out that not all human cultures developed the same mathematical systems. The Piraham people of the Amazon, for example, have no precise words for numbers beyond 1, 2, and many. Their culture gets by with approximate quantities rather than exact calculation. This suggests that mathematics may depend, at least in part, on human needs and cultural development. If that's true, then alien intelligences might have radically different mathematical frameworks, shaped by their own survival challenges and sensory experiences. Still, even if the symbols differ, the underlying truths may converge. For example, aliens might not use base 10 like we do, since that is a quirk of having 10 fingers. They might use base 8 or base 16, but no matter the base, the logic of addition, multiplication, and primes remains the same. The syntax may vary, but the grammar of mathematics persists. This line of thought extends into artificial intelligence as well. When machines learn mathematics, they are not simply imitating human thought, they are uncovering relationships embedded in patterns of data. For instance, neural networks often rediscover fundamental mathematical relationships without being explicitly programmed to do so. This suggests that mathematics emerges naturally from the process of analyzing reality, regardless of whether the analyzer is human, machine, or something else. There is also the question of whether non-human animals understand mathematics. Studies show that crows can count up to 5, and that chimpanzees can grasp simple addition. Honeybees can even recognize the concept of zero, a surprisingly abstract idea. While these abilities don't amount to solving equations, they hint that numerical reasoning is not uniquely human. Instead, it may be a property of intelligence in general, a tool evolution favors wherever survival requires recognition of quantity and pattern. Science fiction often imagines mathematics as the bridge between humans and extraterrestrials. Carl Sagan's novel Contact, for example, features aliens communicating through prime numbers. Movies like Arrival portray alien languages that transcend human perception, but still rely on logical and mathematical structures. These stories resonate because they capture a deep intuition that if reality is indeed mathematical, then mathematics is the one thing all intelligences must share. But this universality has unsettling implications. If mathematics is not bound to humanity, then perhaps we are not the masters of it, only its temporary custodians. Numbers, ratios, and equations existed long before us, and will continue after we are gone. Long after human civilizations vanish, the truths of pi, Euler's identity, and Maxwell's equations will remain etched in the fabric of reality, waiting for whoever comes next to discover them. This raises profound philosophical questions. Do we own mathematics, or does it own us? Are we merely passing through a vast mathematical landscape, mapping small corners of it before fading away? If mathematics is the skeleton of the cosmos, then perhaps intelligence, human or otherwise, is simply the means by which the universe becomes aware of its own structure. And what if mathematics is the key to recognizing other minds? Imagine an alien probe transmitting the Fibonacci sequence or geometric diagrams. We would instantly recognize the intent. Someone out there knows math, and therefore someone out there reasons. Mathematics might be the only truly universal handshake across the void. Ultimately, mathematics beyond humanity forces us to see numbers and equations not as parochial inventions but as cosmic truths. They are not just carved into textbooks or blackboards but into the very bones of stars, galaxies, and atoms. Whether discovered by humans, dolphins, machines, or civilizations a million light years away, the logic of mathematics remains the same. So perhaps we are not alone in using mathematics. Not because aliens are guaranteed to exist, but because mathematics itself exists everywhere. It is the quiet pulse of the cosmos, a song sung whether or not anyone is there to hear it. And if we are lucky, one day we may discover that others too have been listening. For centuries we have described the universe in terms of matter and energy, waves and particles, stars and atoms. But in the last few decades, a radical idea has gained momentum. Perhaps the universe is not made of things at all. Perhaps it is made of information, patterns, codes, algorithms, running like the hidden software of existence. If so, then reality itself might be nothing more than a vast computation, a grand simulation executed by rules as precise as mathematics itself. The seed of this idea goes back to pioneers like John Archibald Wheeler, who proposed the phrase "it from bit." According to Wheeler, every physical thing, every atom, particle, star, and galaxy ultimately derives from binary yes-no choices, the bits of information. Instead of matter giving rise to information, information might give rise to matter. This was not a metaphor for him. He believed the fundamental building block of the cosmos is not substance but information. Today, this view has only grown stronger. In physics, equations like those in quantum mechanics and thermodynamics increasingly point toward information as the bedrock of reality. Consider the famous black hole information paradox. When matter falls into a black hole, it seems to vanish forever. But Stephen Hawking's theories suggested that the information encoded in that matter could not be destroyed, only scrambled. This implies that the universe safeguards information as its most fundamental currency, even when matter itself disappears. From another perspective, the simulation hypothesis argues that our universe is akin to a coded program. Just as characters inside a video game live within a world generated by code, we may be characters inside a universe generated by mathematical rules. To us, those rules appear as physics, gravity, electromagnetism, quantum mechanics. But from a higher perspective, they could be algorithms running on some deeper substrate of reality. Supporters of this idea point to strange hints in physics that resemble digital processes. For example, space and time may not be continuous but quantized, divided into the smallest possible units. Just as a digital image looks smooth, but is really made of tiny pixels, the universe may look continuous but is actually composed of discrete bits of space-time. Planck units, the smallest possible measures of length and time, are like the resolution of reality's screen. Mathematics itself seems to suggest a coded structure. When physicists model the behavior of particles, they often rely on abstract symbols and algorithms that eerily resemble programming. Quantum mechanics, for instance, can be described in terms of probabilities that collapse into definite outcomes when observed, like a computer processing multiple states until one final result is displayed. This resemblance has led some scientists to wonder whether reality is fundamentally a kind of cosmic computation. If the universe is code, then who, or what, is running it? This is where the idea becomes both thrilling and unsettling. Some suggest there could be advanced civilizations capable of simulating entire universes, with our own existence being just one simulation among many. Others take a less anthropocentric view. Perhaps no programmer is needed. The universe might simply be the self-executing result of mathematical necessity, like a program that began with the Big Bang and continues running according to its rules. The digital view of the cosmos also redefines consciousness. If reality is made of information, then minds may themselves be patterns of code, self-referential algorithms operating within the larger computation. This would mean consciousness is not separate from the mathematical fabric of the universe, but an emergent expression of it, just as complex software emerges from simple code. Critics, of course, argue that the universe as code idea is too speculative. They point out that just because reality can be described mathematically does not mean it literally is mathematics or computation. For them, mathematics is a human tool, a lens, not the substance. Yet the uncanny precision of mathematics in describing the natural world continues to fuel the suspicion that it is not just descriptive but constitutive. If this perspective is correct, then reality may not be physical at all. What we touch, taste, and see may be more like outputs of a cosmic program, generated data that feels real because we exist within it. Just as characters in a video game cannot step outside their coded universe, we may never step outside ours, but within it, everything we know is the manifestation of rules and equations playing out at unimaginable scale. The implications are enormous. If reality is code, then perhaps one day we could learn to hack it, to alter the algorithms that govern existence. Physics already hints at this possibility, with experiments in quantum computing showing how information itself can be manipulated to change outcomes. Could advanced civilizations already be altering their universes through such mastery? Could our own future hold the keys to rewriting the code of reality? Even more dizzying is the possibility of infinite recursion. If our universe is a simulation, then what about the universe running that simulation? Is it itself simulated? And the one above that? This cascade leads to an unsettling but fascinating vision. Reality may be layers of code stacked on code, an infinite hierarchy of mathematical programs, each one birthing another. In the end, the universe's code is not just a theory about physics, it is a theory about existence itself, about what it means to be real. If true, it means that the deepest truth of reality is not matter or energy, but mathematics, algorithms running without beginning or end. And whether or not we ever glimpse the hardware of existence, the code continues to execute, line by line, pixel by pixel, generating the astonishing illusion we call reality. For most of human history, mathematics was seen as a tool, a way to measure, count, and predict. Farmers used it to divide land, merchants to calculate prices, sailors to chart their journeys. It was practical, useful, and abstract, a symbolic system designed to represent reality. But over the centuries, something strange began to emerge. Mathematics didn't just describe reality, it seemed to become reality. Equations written on chalkboards predicted phenomena no one had ever seen, and when scientists looked, those predictions were there, waiting, woven into the fabric of existence. One of the clearest examples of this comes from James Clerk Maxwell. In the 1860s, he wrote down a set of equations that unified electricity and magnetism. These equations predicted the existence of waves moving through empty space at the speed of light. At the time, this was pure mathematics, an elegant consequence of symbols, but when experiments were done, electromagnetic waves were found, exactly as the math had foretold. Mathematics had leapt off the page and revealed a hidden layer of reality. This was not a one-time miracle. Again and again, mathematics has anticipated discoveries long before our senses or instruments could confirm them. Paul Dirac's equations predicted the existence of antimatter before it was ever observed. Einstein's mathematics of relativity suggested black holes, gravitational waves, and the bending of light by mass. Decades later, telescopes and detectors proved these predictions true. What began as abstract symbols became concrete phenomena, as though reality were obliged to follow the script written by equations. Such uncanny success forces us to ask, is mathematics invented or discovered? If it were only a human invention, why would it align so perfectly with the universe, often in ways beyond what we could have imagined? If it is discovered, then it must already exist, woven into the structure of reality itself, waiting to be uncovered like a hidden law of nature. When math becomes real, it suggests that numbers, patterns, and equations are not just descriptions of the world, but constitutive elements of it. This perspective has led some physicists and philosophers to argue for the mathematical universe hypothesis, proposed by cosmologist Max Tegmark. It suggests that the universe is not simply described by mathematics. It literally is mathematics. Every particle, every law, every interaction is part of a grand mathematical structure. The equations are not a map of reality. They are reality. When we solve them, we are not inventing truths, but revealing the underlying scaffolding of existence. Consider the case of string theory, one of the most ambitious attempts to unify physics. Though still unproven, it is a purely mathematical construct that suggests all particles and forces arise from the vibrations of tiny strings in multiple dimensions. The mathematics of string theory is breathtakingly complex, far beyond everyday experience, yet it may provide a coherent description of the universe. If proven, it would mean that the deepest reality is not made of stuff at all, but of patterns described by mathematical vibrations. Critics might say we are confusing the tool with the territory, mistaking our descriptions for the world itself, but the repeated power of mathematics to uncover truths we had no other way of knowing is difficult to dismiss. Unlike a hammer or a wheel, mathematics reveals things that seem to exist independent of us. The Higgs boson, for instance, was predicted decades before it was finally detected. Equations whispered of its presence long before machines could confirm it. The notion that mathematics becomes real also challenges our perception of what is physical. If equations can dictate the very existence of particles, then perhaps reality is less like a solid stage and more like a story unfolding according to mathematical rules. It is as if the universe were a vast novel, and mathematics is both its language and its plot. This idea resonates even in everyday experiences. Think of music, which is fundamentally mathematical in structure, frequencies, ratios, harmonics. Yet when we hear it, math becomes emotion, resonance, memory, or consider architecture. Abstract geometry transforms into cathedrals, skyscrapers, and bridges. In these cases, we witness math becoming real, not in distant galaxies, but in the spaces we inhabit and the lives we live. If mathematics continues to reveal itself as the foundation of reality, the implications are staggering. It means that our quest to understand existence is ultimately a quest to solve an equation, perhaps the ultimate equation, one that unites every law of physics. Some dream of a theory of everything, a single mathematical framework that explains why the universe exists and why it has the properties it does. If discovered, it would be the most profound instance of math becoming real, the unveiling of the equation that generates reality itself. Of course, there is also humility in this pursuit. Our equations are products of human minds, shaped by culture, language, and limitation. It is possible that reality's mathematics is deeper, stranger, and more intricate than anything we can conceive. Even so, each time math leaps into reality, from Dirac's antimatter to Einstein's black holes, we are reminded that our symbols are not arbitrary, they are resonances with the very heartbeat of existence. In the end, when math becomes real, it transforms our relationship with the universe. We are not merely observers describing what we see, we are participants in a grand mathematical unfolding, beings of flesh and thought who are themselves patterns in the equation. Reality is not indifferent to mathematics. Reality is mathematics, embodied, expressed, and made manifest. And as long as we keep asking questions, writing equations, and seeking answers, the line between the abstract and the real will continue to dissolve, until perhaps we discover that the two were never separate at all. From the first whispers of mathematics in ancient dreamers, to the dizzying frontiers of modern physics, one truth has echoed through every age: numbers are not silent. They speak, they shape, they predict, and perhaps they are. We began with myths and visions, when early humans carved notches into bones to count their harvests, never suspecting that these same marks were the first footsteps toward understanding the universe itself. Plato envisioned perfect forms, abstract realities more real than the shadows of matter. Galileo saw mathematics as the very language of the cosmos. Kepler revealed harmony in planetary orbits, while Newton built a clockwork universe wound tight by equations. From symmetry to constants, from relativity to quantum mysteries, mathematics has been the consistent thread weaving through centuries of discovery. But the deeper we've gone, the stranger the fabric has become. Quantum mechanics showed us that reality is not continuous but discrete, ruled by probabilities and wave functions. Chaos theory revealed that even apparent disorder hides subtle equations beneath it. Information theory suggested that reality might be better understood as data than as matter, and simulations, once science fiction, now hover as legitimate hypotheses about the very structure of existence. Each time mathematics steps forward, the ground beneath what we thought was real shakes. Each time an equation predicts something unseen, antimatter, black holes, gravitational waves, and experiments confirm it, the line between abstract and physical blurs a little more. We are left wondering, are we discovering the laws of the universe, or are we deciphering the very code that is the universe? Patterns in biology. The Fibonacci spirals of seashells, the branching of trees, the rhythms of the heart, all whisper the same truth: numbers underlie life itself. Fractals stretch infinitely into the horizon, mirroring the structures of coastlines, galaxies, and neural pathways. The universality of mathematics suggests that it is not bound to human thought. If aliens exist, their art may be different, their languages strange, but their physics, their chemistry, their equations, those would be ours too. And so we arrive at the paradox: is mathematics a tool of human invention, or the skeleton key to the cosmos? If invented, why does it work so uncannily well in revealing truths far beyond imagination? If discovered, why should human minds, fragile, finite, and born of survival instincts, be capable of touching such vast and eternal truths? The answer, perhaps, is that we too are part of the equation. Our thoughts, our minds, our questions are not outside of the universe but inside it, generated by the same mathematical structures we seek to understand. We are patterns looking back at patterns. This realization can be humbling, but also profound. If the universe is mathematics, then our lives, our choices, even our dreams are expressions of equations too complex to fully trace. Yet, that does not make them meaningless. On the contrary, it makes them extraordinary. Waves in the great ocean of reality's formula, unique manifestations of the infinite possibilities embedded in the code of existence. The search for a theory of everything is at its heart the search for one ultimate equation, a single, elegant framework that explains all forces, particles, and phenomena. Some physicists believe this equation exists, hidden but inevitable. Others argue it may forever remain out of reach. But the pursuit itself reveals something important. Mathematics is not a backdrop to reality. It is the stage, the script, and the performance. When we do mathematics, we are not scribbling abstractions, we are tracing the architecture of being itself. And so, after 30 explorations from Plato to fractals, from Einstein to information theory, we circle back to the haunting possibility: reality could be nothing more than a mathematical equation. A vast, timeless structure where every constant, every symmetry, every law is not accidental but necessary, where the universe doesn't merely follow mathematics. It is mathematics. If that is true, then we too are equations written in flesh and thought. Our laughter, our grief, our triumphs, and our failures are not separate from the laws of physics, but are expressions of them, ripples in the grand formula that sustains existence. Perhaps this should terrify us. Perhaps it should comfort us. Perhaps it should inspire us. For if we are equations, then we are also solutions, temporary, beautiful, fleeting manifestations of the infinite. In the end, whether you see mathematics as invention or discovery, tool or truth, one fact remains: the deeper we go, the more it reveals. And somewhere, hidden in the complexity, may lie the ultimate revelation that the universe is not a place we inhabit, but a formula we are living out. A proof, infinite in scope, written across time and space, a story told in numbers, waiting for us to keep reading. So next time you look at the stars, remember those points of light are not just fire burning in the void. They are equations shining, mathematics glowing, reality itself made real, and you standing here, questioning, calculating, wondering, are part of that same equation. You are both the observer and the observed, both the question and the answer, both the symbol and the substance. Reality could be nothing more than a mathematical equation. But if so, it is the most beautiful one ever written.